And you're the only thing I think about. It's all that I can still do. And you know you're the one I dream about. I couldn't do without you.
Good morning. Welcome to the Great Hall. Welcome online. It is really great to see you here. So my job really today is just to welcome you all both in person and those watching the live stream. I have to say this event has been long planned and replanned and replanned and replanned. So it is fantastic we're actually able to be here in person today. I'd like to just start, before having a few thank yous, just by apologising to one or two people who may be listening. We've been delighted by the interest in the event, that people want to submit posters, give talks. As you can imagine, we've been a bit restricted in numbers, which is why not all of you could be chosen, but they were all extremely good posters. We'd like to have everyone, and next year we will hopefully do that. But before we start, I'd like to just do a few thanks. Firstly, a thanks to the events team who have been ushering you in this morning for actually enabling us to put this on. It's been an enormous amount of work from them, and we really are very, very grateful. For our external speakers for coming up and visiting us in Leeds, thank you very much indeed. It's a real pleasure to have you here, and I'm delighted that you can actually come and see us in person, so enormous thanks to you. To the Bragg committee, who have all of us together have helped arrange the schedule for this, and of course the Royce Institute, of which we're a part, and the work of the Bragg is one part of our work in the Royce Institute. But I think before I finish, the two people I really want to thank are Andy down here and Lucy somewhere, I can't see her from here, who really have put all this together, and I think we have enormous thanks to the two of them for really trying to sort this out, make all the arrangements in these really difficult times, rearrange, and rearrange. So Andy and Lucy, thank you very much. And before we start, let's just give Andy and Lucy a round of applause, please. So with that, it's a pleasure to hand over to Professor Nick Plant, who is our Deputy Vice-Chancellor for Research and Innovation. Nick.
Thank you very much, Edmund, and welcome everybody. There is one person that was missed off the thank you list, and that is Edmund himself. I would echo the thanks to the conference team, to Lucy, to Andy, but also very much to Edmund as the driving force and director of the Bragg Centre. He really has been pivotal in doing something that actually no other research centre across the university has done yet, which is to bring us back in person in a meeting to talk about research. And I think that is amazing. I am genuinely getting goosebumps standing here. I've not stood in front of this many people for 2 years, and it's wonderful. It's really nice to see people who are keen, who are both internal and external, come here to talk about the thing that really drives them, that they are passionate about. So thank you for all coming. For those people listening remotely, I think the other wonderful thing that we've been able to do through the pandemic is actually develop electronic systems that are capable of allowing us to have these sorts of hybrid meetings. Because what that does is that allows us to reach more people. It allows us to lower the barriers to people to take part in conferences such as this and to gain the benefits from it. So I think as an approach, it's absolutely wonderful. So this is very symbolic for me and really important, but I think the Bragg Centre also deserves a lot of plaudits. Despite the fact that the Bragg Centre itself has been birthed through the COVID pandemic, it has gone from strength to strength. Edmund, Andy, the whole Bragg management team have worked really hard to build the Bragg brand, to move into the brand new Bragg building, to really see the fruition of our partnership with the Royce Institute. And what we're now starting to see is the real momentum that is being gained from that. In the last year, we've got a 50% increase in members of the Bragg community, and I think that's really tantamount and testament to the work that's been done by the whole Bragg team to really engage and pull people together. So I think you're going to listen to some absolutely wonderful science today, but I think the most important thing is science is wonderful, community and talking about it is even better. And one of the other things that I think Bragg has done really well is that outreach, that conversation with people from the wider community. So I know yesterday there was an outreach with some school children doing the DNA origami that Andy's very famous for, and you're going to hear more about it later on today. That's one example of the work that Bragg does, but it does much other things, reaching out to different communities to talk about the importance of material science. And I think it's something that genuinely sits at the bedrock of many other technologies, many other approaches that will solve the global challenges of today. It's absolutely key that we get people like you in a room to talk about the things you want to do, to talk about those challenges and push the boundaries. So I am absolutely delighted to be able to open today's exchange so you genuinely can brag about materials research. Thank you very much indeed. Andy.
Thank you very much, Nick. I feel wildly underdressed in comparison to everyone else. So yes, I just want to reiterate briefly, thank you so much for coming. It's wonderful to see you all in person. And without further ado, I'm going to do the dirty job of doing the housekeeping before we proceed into the talks. So unfortunately, I just want to cover the quick basics. Face coverings, for the health and safety reasons, we are asking that you do keep them on while you're seated. Otherwise, while you're drinking, that's okay. And if you're talking, obviously, then please remove them. Toilets, for anyone who needs the toilets, there are no toilets upstairs. They're all downstairs, so you have to go back down and to the left of the stairs. There'll be events team downstairs to help guide you. If you need step-free access, then that can also be guided through the back here. Catering, we are at lunchtime all heading over to the refectory. If you're lucky enough to be wearing one of these beautiful lanyards, then you will be escorted to the VIP lunch, which is in the Sugden room instead, and everyone else is going to be escorted across to the refectory where a hot buffet is being served. Emergency, I am told that the fire alarm which was scheduled for this morning is actually moved to tomorrow, so it's already passed, but we're not expecting any fire alarms at all, so if there is one, then we need to evacuate, and the assembly point is out the front. The events team and the Bragg team will help escort you if such an event occurs. And I think it's very important, in the spirit of our new ED&I framework that we've adopted, you should see the code of conduct printed in the front of your guides as well, but it's important that we note that this is an event that is inclusive to everybody, and everyone needs to feel welcome and that their voice can be heard. So I'm not going to read through this. You will have a copy of it in your agendas, but this is something that you will see at every single event that the Bragg puts on in future. And that's it. So without further ado, I'd like to welcome Tom McLeish up to the stage to open our first session. And our first session is on soft matter.
Thank you so much. Well, Andy, thank you, and Ed, everyone, it's a real pleasure to be here. It is great. As some of you will know, this particular place is also very special for me. So I was enormously privileged to be a professor here at Leeds for about 16 years, and that was some while ago. So it's been huge. It's been wonderful to meet some old friends again. I've not been here for a few years. And we looked at each other, and we all would have very much liked to have said, "You haven't changed a bit." But the words kind of wouldn't have been true, were they? But you know, but time passes for all of us. But science continues to grow and is very, very rich. I remember, particularly, I'm a little bit early, so I can get a few of these remarks in, can't I? This is a very, very special university, a very special place, and just one memory being here at graduation ceremonies. I remember the last time I was standing right actually at this lectern was to speak on behalf of Professor Dame Julia Higgins, to whom we awarded an honorary degree at Leeds, and of course a wonderful materials scientist, physicist from Imperial College, real pioneer in so many ways with Julia. The other honorary graduates at that ceremony were Wally Sowella, who is, I think, Leeds' still probably only Nobel laureate, and a privilege to meet the only academic I know who's actually gone to prison this is for his academic work, and that you know, being here and seeing him speak for his wonderful African literature, do read him if you haven't. That was a real privilege, and of course the other honorary graduate was Ian McKellen, aka Gandalf, for those of you who spoke on behalf of the graduands and recited from memory in a wonderful speech from a less very well-known play of Shakespeare's, where Thomas Merton gives a speech against immigrant haters. And it's in a Shakespeare play because this is a subject which never goes away. And it was wonderful to hear the echoes of the greatest of English writers morally resounding in this hall over 4 centuries, reminding us, you know, that if, as Merton did do in Trafalgar Square to calm a riot, it was the Portuguese back in 1590, then that was the issue, that if those of us who refuse to offer a home to the stranger do not deserve a home when we ask, when we're on the run, and when we are homeless. And so that, you can imagine that that memory is a very special one. So I have huge, but that's just one of the reasons that I have to thank this university for. The others will appear now, because we're going to explore some soft matter materials, interdisciplinary materials science together, and I'd just love to share with you for 20 minutes or so a yarn, excuse the pun, of some work I've been doing on the nature's most marvelous material, that is silk, a material that has been at the nexus of a relationship between human beings, spiders and silkworms and their flies for thousands of years, as far as we know. A material responsible for global trade routes, for technologies, for cities like this one. You know, so natural and human-made fibers are part of the DNA, excuse that pun again, of this place. This is work, by the way, that I've been privileged to do with my postdoctoral colleague, Charlie Schaefer, who's from the Netherlands. It's honestly, you know, it's of course 10% of me, 90% of Charlie. We'll meet Charlie a little bit later on. Thanks to the EPSRC, to the Physics of Life group at York, and to the Physics of Life Network UK. I just thought I'd just remind you why this talk is very much part of the DNA of this place. I was talking with Ed yesterday, and although there's no sense of copying here or modeling, there is the idea of interdisciplinary networks at this university has been well established, and the Astbury cluster or network, to which I belonged when I was here, got me going on thinking about the polymer physics of life's polymers. When I was here, there's William Astbury. Astbury, of course, responsible for some of the first X-ray scattering from DNA, but it was DNA fibers. Well, of course, the Braggs were here. The work of the Braggs permitted and developed that wonderful technique of structural scattering. And so structure and biomolecules, and particularly biofibers, all those come together right here. They really are part of Leeds proteins, if not Leeds DNA. You might, the whole idea of a topic called molecular biology was invented here. Good place. Well, I thought, you know, for personal motivations, I realized, reflecting, why I ended up studying silk and the physics of silk formation, and why, you know, it was really inevitable that I did so. For those decade and a half that I was working here, I suppose I could say there were 3 main aspects of materials physics that interested me. The first was my long-term interest in collaboration. We had a huge project here, multidisciplinary, with chemistry and physics and mathematics and computing and the polymer and plastics industry. And this was trying to build in silico from molecules up to materials processing models for polymer viscoelastic flow. So we could understand the physics of how engineering at the macromolecular scale, with different chemistries and particularly different degrees of branching, in my case, gave rise to viscoelastic properties that covered an enormous palette of different flow properties, and which determined whether or not with certain plastics you could make fibers or films, or whether injection molding would work, and so on. And it was, I have to say, it was huge fun, and thanks to support from EPSRC and industry, you made a huge amount of progress and work done here on that molecules to materials processing ladder is now embedded in the way that industry designs new polymeric materials. And although, of course, at the time, I am, of course, overwhelmed with guilt for having enabled the oil-based plastic packaging companies to be quite so successful in a tiny way. But because of the universality of all that physics, that science is now being directed towards biomimetic, sustainable plastics and short-circuiting the recruitment of new biological materials into the oil-based plastic sustainable materials economy. So that's very exciting. A second area I was very excited about was polymeric self-assembly, the extraordinary way that macromolecules can encode in their, as it were, alpha structure, emergent properties. So examples are foams and very resilient composites of self-composite materials, so they're both strong and tough, that have two components, perhaps copolymerized into the polymer chain, as you see on the top right there, which give rise to fascinating morphologies that can be controlled, as the diagram extreme on the right there. In fact, by the way, that was the collaboration we had with Julia Higgins's group, who was fascinated in block copolymers and all that they do. And then thirdly, this is the place where I learnt that if you know something about the physics of polymers and self-assembled surfaces and foams and membranes, then it might be worth having a discussion with biologists, because life has evolved the use of macromolecular materials in both the structural and the functional, and indeed the coding aspects of life itself. And I became very interested in protein dynamics and how Brownian motion affected information transfer in molecules. So if you put together viscoelastic flow, self-assembly of materials from polymers and bioprotein physics, what do you have? You have silk, because silk is all that. Silk is a material that within the silkworm is in a viscoelastic macromolecular polymer solution state and is switched into a crystalline protein fibrous state by flow alone, by an extensional viscoelastic process, just like, well, turns out a little bit more fancy than, but very, very much like the extrusion processes being adopted and developed by the companies we were working with here. Of course, there are many subtleties to the structure of silk fiber. There's a gluey, tough skin to the silk fiber, which is dominated by a protein called sericin. But the main structural component of a silk fiber is the protein fibroin, which is convergently evolved across many, many species, and here they all are, and is running down the center of the fiber. We might think, there's a few spiders and the odd worm that makes silk. There are dozens of species that have convergently evolved this extraordinary material. I mean, there's just some of the pictures of them there. There are the arachnids, obviously. There are many insects too. But the fundamental molecular structure of silk, with some variety, persists. I know you'd be very disappointed if I didn't show you a picture of a big scary spider. There's a picture of a big scary spider, and we're working with the theory stuff that I do with Charlie. We've had a very, very productive collaboration with Chris Holland's group in Sheffield, and Chris started his work on fibre silk with Fritz Vollrath in Oxford. I was very amused to learn that the first thing you had to do in Oxford, when Chris was working for Fritz, if you're going to work on spider silk, is to overcome any arachnophobia you might have. All the new students were sent up to the spider greenhouse on the roof on their first day. Great big mothers they really were. And you have to be able to pick them up and milk them of silk. They use silkworms now for all sorts of reasons, and there's less screaming involved, I understand. So fibrin is mostly quite a simple polymer. I mean, you know, this is a big engineering production plant this little silkworm has. It can't afford to use very fancy amino acids, so it just uses bits of glycine, serine, and alanine, mostly. But with a little bit of added fairy dust. We'll come on to that in a minute. I knew Ed would murder me if I didn't put up a proper, you know, material science strength and stiffness plot. So there's the material science strength and stiffness plot. So I've acquitted myself. But you can see with ceramics, and I've got some metals there, and tungsten and hydroxyapatite for good leads polymer purposes too. That's in the middle of the plot. But see where the silks are. The silks are that pink oval at the top. Just as stiff as steel, if not a lot stiffer, but orders of magnitude stronger. I mean, they are extraordinary materials, slightly pipped at the post by Kevlar. So, how does this happen? There's another issue, and this is one of the most interesting issues. Now, this is an experiment done in Chris's lab, comparing an ordinary flow crystallizable polymer, it's high-density polyethylene, and spin fibers with that, and when the polymer molecules align, the flow, you can imagine the polymer strings, you imagine what flow does, that extensional flow, the flow has handles on the molecules, the strings align, and then they can crystallize. You can't crystallize very easily polymers in their entirely random walk state. They've got to align into the crystals. So this is a plot against shear rate of shear induced crystallization with measure of the specific work. Now, I remember what got me into what got me into polymer science in the first place is the gap year I spent before even going to an undergraduate physics degree, working for a fiber spinning company in Coventry called Courtaulds. If you're very old, I mean, you'll remember Courtaulds. It's the same Courtaulds as the Courtaulds Art Institute in London. And like many British chemical materials-based companies, it went to the wall a long time ago. But I remember seeing solution spinning of fibers at the Courtaulds production plant. And I do wonder whether that memory stayed in my mind as resurfaced in this silk project. It is an aesthetically beautiful process. There's a spinning plate with about 30,000 tiny little machined holes through which the polymer solution is forced at immense back pressure, and out come 30,000 little tendrils into the solution, and as the solvent is released from the polymer solution in the fibers, the polymer gets more concentrated, and this extraordinary yarn web of fibers emerges. It's a highly energetic process. It needs, when you start doing the sums for silk as a solution spun polymer, what back pressure you'd need and how much work and energy you would need to employ to make silk, you calculate that the silkworms and the spiders should explode. It's just not possible for a biological compartment to hold that sort of massive back pressure and do solution spinning. But when you try it in the lab, you realize that actually there are rates at which there's practically 2 orders of magnitude less energy needed to spin silk than to spin human-made artificial fibers. And this is a polymer melt, but it's all weight for weight. So there's something about silk which means that the energetics are between 1 and 2 orders of magnitude smarter and more efficient than anything that we've been able to do. We need to get on the warpath with that. So what is the molecular viscoelastic polymer processing science of silk? Here's a clue. I said that there were boring amino acids along the fibroin sequence, but here's just a little. What we've done here, what Chris has done is to plot positive and negative charge groups and where they are along the amino acid sequence. Can you see there'll be aspartame or glutamate, arginine, lysine, histone at the top. Now, can you notice 2 things? One is at the beginning and end they cluster, and there's an extraordinary, breathtaking regularity in the sequence of charged groups along the silk protein. And in this particular case, which is the Bombyx-Maury version of fibroin, can you see that the positively charged side groups are immediately adjacent to the negatively charged side groups at almost every place in charge balance. So you have little dipoles. So if you're a polymer physicist and you're interested in viscoelastic flow based on molecular science, what's the model we use? We know the most important piece of physics from which viscoelasticity emerges from polymers, and that's the entangled physics. So I've got a standard picture down the bottom left-hand side of the model that's been developed now for decades, which captures the physics of statistical random polymers, where elasticity just emerges from the connectivity of the polymer, but they're overlapping in such a way that their topology dominates their dynamics. You see, if I'm a string and I'm entangled in a bath of molecular noodles with lots of other strings, I can wiggle along my own length very easily, but I can't go sideways because I can't unknot and pass through strings next door. It is knots in 3 dimensions, a mathematical result. So we model that with a tube. You can see there's a sort of, it's effectively like a sleeve. I mean, it's just like this sleeve here. So I'm a polymer doing random motion. The only way I can get my jacket off is just, I can't, other than tearing my sleeve, is to just wiggle about until I shake my arms out of the tube of the jacket, you see. So there's the demonstration of how polymer viscoelastic works. But that model on its own won't do. For silk, we want to add one more thing at a time. Now, there's a little story here, which I also learned when physicists start to work with biologists. Arguments happen about adequacy of models. And I learned very quickly that molecular biologists have a respect for detail and completeness, which I also respect. But you know what physicists do? We quite like to ask, well, what's the minimum model we can get away with? And I remember being told I was reinventing the spherical cow a 1,000 times. But okay, it's a spherical cow of fibroin. It's an entangled polymer with regular charge groups along it. We're going to run with that and see how much we can learn. And if we need to put in more detail, then we will. Okay. Rheology, or mechanical spectroscopy. I have to show you a mechanical spectrum because otherwise I'm not doing justice. For 16 years at Leeds, looking at thousands of these measured just down the hill there in the physics department. Mechanical spectroscopy, you take a rheometer, you've got 2 plates, you put your sticky liquid between the 2 plates, and you slide them, either rotate them around each other or wiggle backwards and forwards. You're doing spectroscopy, but with shear. And you impose a slow frequency on the material, and then you scan to higher and higher frequencies, and you measure the elastic response. And if it's an elastic solid, the stress is in phase with the strain, and if it's a viscous liquid, the stress is in phase with the strain rate. But a general viscoelastic solid will have an in-phase component and an out-phase component. So there's the log of the frequency, and the red curves are the elastic in-phase component of the stress against frequency, and the green curves are the out-of-phase viscous part of the response. And now's not the time to go. If those of you who've seen these plots and know how to interpret them will be on this already and far ahead of me. Those of you who don't worry, that's all you need to know. But just note that at low frequencies, as you might imagine, which is dominating? It's the potty-putty effect. If I let a viscoelastic material flow very slowly, I see its liquid character. It flows into puddles, and sure enough, the green viscous component is dominating. At high frequencies, I can take my potty-putty and bounce it, and it's elastic, and sure enough, the red component is there. This is silk. The data there, Pete Laertes and Charlie's and Chris Holland's measurements on silk. And what the other piece of information you need to know is in the imaginary part, the viscous part, the green part, if there's a single relaxation mechanism, there'll be a peak. But you can see I could probably model that shoulder by sort of two peaks, one to the left where the curves are crossing, and one where I've got sticker lifetime. There's another little shoulder there. And if I compare this to an ordinary polymer melt, that right-hand peak is new. But the left-hand peak just looks like the process of wriggling out of my sleeve that all polymers do. We can watch them wriggle out of their sleeves, and there's a time for that. It's called the reptation time. And there it is. It's where there's two halves cross. But there's this extra relaxation process there. The curve through that is an almost parameter-free model of a sticky polymer. What these charge groups will, of course, do is stick to each other. A dipole will stick to another dipole. A monopole will stick to another monopole with a calcium bridge. We didn't invent this idea. Stan Leibler, Mike Rubinstein, Ralph Colby wrote some of the works on the sticky polymer case, sticking can polymers in the 90s. But there was very little experimental work, some on artificial polymers with occasional charged associating groups. But this is the first time a natural polymer had ever been identified as being well approximated by a sticky reptation model. And we discovered we could do much more with it, because if you know that these stickers are charged groups, and you know what those charged groups are, and you know their pK, and you know the charge background, and you know the activation energy for breaking and making the bonds, you can make predictions not just for that free mechanical spectrum at one temperature and one solution. You can make predictions without changing anything else for a range of temperatures on the left, where the viscosity changes, and a range of salt concentrations on the right. And it changes. Aha! Another aha. Because not only is this a really interesting case of a viscoelastic fluid with stickers that offers enhanced viscosity, but that viscosity is controllable by temperature, by pH, and by salt. And that's going to be interesting. And sure enough, you do have to dissect the worm to do this, but if you measure the pH and pK along the spinning duct in a Bombyx mori silkworm, you'll find that the pH and the pK of calcium is locally controlled at different points along the spinning pathway, the extrusion pathway. So this is more advanced than any fiber spinning process that people have ever made. It's exquisite. You have flow, rheological, and chemical control at every point on the pathway. What could you do with this? Now, that's the linear response. I should say that first section was all about linear response. And the last part of this story, up to where we are now, is, of course, the nonlinear, strongly stretching response. As I said, we can tickle a polymer and measure its viscosity, that's fine. But if we want to understand what happens when this material is extruded by hundreds or thousands of times and stretched and turned into a fiber, we've got to go heavily nonlinear. Now, the nice thing is, partly because of work done here over all those years, we have quantitative models for nonlinear response of polymer processing materials too. And we know that extensional flow does what I waved my hands before. Now I can show you the picture. The tubes stretch, everything stretches, the environment stretches, and the chains stretch. And if you think about it, strongly oriented, I could have looked at that charge sequence, evolved charge sequence with those regular spacings, and guessed straight away that the point of the fitness that promoted the evolution of that regularity has to be an alignment process of the chains. Because even if you've got regularly spaced somethings on a polymer, if it's a random walk, that regular space of the sequence is not reflected in any spatial structure because the spatial walk is random. However, if I stretch or just align the polymer out with a little bit of force, then the regularity of those charge groups, look at the red blobs, along the sequence becomes a spatial regularity, and I can do structural things with it. On the other hand, the prognosis is not very interesting. It's rather boring, because what we're going to be doing with nonlinear flow is having little bits of segments that stick to each other temporarily and polymers between them, and then the junctions will break, and then they'll flow a bit, and they'll stick with other neighbors over here, and they'll flow about a bit. That's called the transient network model. They were working on it in the 40s. We used to teach it, graduate, lecture 1, and you sum over all the chains, and you do a pre-average, and you get this differential equation called the upper convected Maxwell model for the stress. It's phenomenological rheology 101. It has a single relaxation time, yada, yada, yada. And when you stretch this thing, if you stretch it slower than the temporary junction time, then the temporary junctions will just allow the chains to relax, and you'll go to a nice smooth plateau stress, and you'll have a well-defined viscosity. If, however, your extension rate is faster than the relaxation time, then the chains on balance keep stretching and keep stretching and keep stretching, and they just run away and run away and run away till something breaks. You don't get a viscosity at all. Gotcha, right. So we know what's going to happen. Dull, 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 dull. But wait. Wait. That was all calculating for the average. Suppose we do this theory properly, even at this coarse-grained stage. Suppose we calculate the distribution function under a flow for which molecules have been stretched and which not. Because after all, what's going to happen is, suppose I take the simplest case of a chain with just 2 stickers at each end. It can either be a chain belonging to the network, that's the top one, or it can be a chain free, it's disconnected with the network, the bottom one. The bottom one can relax, and the top one's going to stretch, because it's tied to the network that's stretching. Now, maybe there are lots of different stretches. Maybe there are some molecules that end up not very stretched, and some. It's a bit like, think of a crazy drunken party at the London Underground. There's an escalator going up and an escalator going down, and there are people jumping from one to the others, and some are going up and some are going down, and people end up all over the escalators. Some towards the top, very highly stretched, some at the bottom. You'll see. So we have proper mathematics for distribution functions. The top one is just stretching, and the bottom one is stretching and retracting. Never mind about the details. What happens is breathtaking. There is a steady state solution to that, and it's a power law distribution in stretch with an amazingly long tail. The probability of a stretch lambda in the tail of the distribution goes as lambda to the minus a power. That power law is an interesting scaling function, hyperscaling function of the lifetime of the stickers and the flow rate. It's an interesting function, but you can control it. And that analytic result are the black curves, and the points are Charlie's simulations. And the time dependence is really interesting. Can you see the crazy drunken party hopping? There's a stretch with time. So chains hop on and off, hop on and off, and they escalate to the top, and they hop onto the down escalator, and they come down again. It's very sporadic, but at any one point, I've only stretched perhaps 1% of the chains get stretched 100 times right down here. Oh. How could I have managed to crystallize a polymer solution spun fiber at 100 times greater efficiency. Well, I realized actually, I don't need to stretch all the chains. I only need to stretch 1% of the chains, because then they act as nuclei for the others, and all the energy I can get out of the latent heat of crystallization. But how could I be clever enough to have a flow that only stretched 1% of the chains? Stickers will do this. And they created an entirely, there's a whole phase space of flow rates and relaxation times in which you can map out different regions where the mean stretches, or just you have a highly stretched variance. And then you can do it properly, because Charlie's done this wonderful simulation of much more faithful chains that can't be analytically solved, but you can vary the number of stickers, you can put entanglements in, you can put finite stretch, because of course you can't infinitely stretch a polymer, but the same thing happens. The underlying physics of stretching a tiny fraction of the chains so that they could act as a nucleus to crystallization survives all that process. And when you calculate the critical work to align a fraction sufficient to nucleate a crystalline fiber, this is the work against the flow rate. Can you see, ignore there's various other hypotheses here, but follow these blue circles here. There's a super sweet point, which is up to 2 orders of magnitude more efficient than the rest of the process. So evolution has done this wonderful thing. And I have to say, this is a really interesting lesson I have learned in working with biology as a soft matter physicist, that though it is true that one can shed some light on biological questions with physics, the gift in the other direction, in which biology turns up and discovers through evolution new physics, is remarkable and consistent. So to summarize, here's our overview. That we have, there's now the silk duct there. I said that early on in the silk duct, one gets this orienting flow. In fact, that's the place where the viscosity is tuned low, so it doesn't take too much work. And then just when you need to stretch the change, the viscosity kicks up because of the salt concentration and pH, and there it's stretched, and out you make the fiber. And the outlook, of course, here is what a lesson for bio-inspired materials. Can we be as clever as silkworms? It remains to be seen. There's Charlie. If you're interested in this, all the software he's invented is up on GitHub for free. Huge thanks to Chris and Pete at the University of Sheffield, to Daniel Reed of this parish, Richard Graham, Tom O'Connor for fabulous conversations over the last couple of years, and to EPSC funding. And thanks very much for inviting me here. Tell you about the story.
Wow. A wonderful starting talk. Thank you very much, Tom, for opening. So have we got any questions for Tom? I do suspect that there are some lovely new dance moves on
There's
YouTube.
a man with a question over there.
Can we run a mic down, please?
Hi, Tom. Fascinating as
Hello,
ever.
great to
So
see
one
you.
of the things I remember from a while ago is that if you actually try and make your own polymers, your own kind of spider silk, it's about 10 times worse than the spiders manage. So is there something subtle in the way that they kind of do the processing? I think you probably hinted on that.
Yeah.
That gives you a much stronger material.
Yeah, I think so, Oliver. I think that's right. Because typically what we don't do, we don't control both the pH and the pK all the way locally, all the way through the spin channel. And if you don't do that, you really do mess up. Because you don't get in the right regimes at the right place, you don't stretch the right fraction. So it's a highly, I don't know if you noticed just how sweet in terms of reduced flow rate, the Weissenberg number. This is Weissenberg number in terms of a relaxation time, which is a combination of reptation and sticker lifetime. You've got to be bang on there. And not only do you have to be bang on that point, but you have to control the through line history. And as far as I'm aware, those experiments simply don't do that. So the research program that I don't think anyone's done, which is just be gorgeous to do, would be a microfluidic program in which pH and pK is controlled by cross-flow at various points in the duct, and that will also address the problem. I've asked microfluidic people, why haven't you done this? And the answer is because the viscosity is too high. Well, the viscosity is too high is because you aren't doing what the spider does at the right points and making sure that you use the pK to keep the viscosity low. I think that's the answer. Great question.
Right.
Thank you. Down the front here. Down.
Tom, I could really see the extrusion with your animated talk. So it was fascinating. Just a question about your slide on the comparison between HDPE and silk. What is your feeling on that? Do you see a future there in terms of replacement of HDPE with silk? So just a random thought.
Well, yeah. So this is the experimental evidence that it is indeed the case that this mechanism, and I think we've more or less tied it down to this process, convergently evolved across species, allows super efficient spinning by creating nucleating agents, fibrous nucleating agents, which are only a tiny fraction of the overall population of chains. That's the mechanism. So yeah, if we can find out how to do that, then that opens up a whole new sustainable industry, which is not only, which is sustainable because it's using biological feedstock and biomimetic materials production, but it's also biomimetic in its efficient processing. Then just go back. I mean, can you use this process in injection molding? Can you use these types of materials in film formation? I mean, I've no idea. Nobody knows. Or what other dimensions to this are there? Are there temporary network, temporary rheology one can create along the branching side of things, the hydrophobic side of things? There's along the formation of secondary structure. What suppose you want to make helices? Because eventually, by the way, there's a whole beta sheet story going on here, which I didn't have time to touch. But you're absolutely right. Fantastic question. The vista is open right now.
Thank you very much. Are there any more questions? Yes, Rick.
Is there a way you can sort of back out what the critical nucleus size might be from this sort of model?
Yes, that's a really good question. Of course, did you want to say something else? Yeah. I mean, the critical nucleus is, it looks as if the critical nucleus is at least a local or semi-local bit of very highly stretched chain. Now, there are, as Oliver Harlan knows very well, and this is another story that started here. There's a big international program on understanding the HDPE and the crystallizing polymers, and what is the shape and size of the nucleating crystal there. Richard Graham, again formerly of this parish but now at the University of Nottingham, is probably a UK leader here, together with Daniel Reed at the Maths Department here. And so the answer is yeah, one could back it out. Right now, I should be super honest and say that the simulations that you saw of the multi-sticker silk are not yet properly entangled physics. It turns out that might not make that much difference when you have very, very highly oriented solutions. But before we can be quantitative about that sort of question, we do need to to model the whole entanglement field and put that in. But the answer is in the fullness of time, and when we believe that the physicist's rough spherical cow model is faithful and close enough to the biology, quantitative enough, then yes, absolutely.
Thank you very much. So I think we'll channel any other questions into the break. So if you'll join me in thanking Tom again and for a wonderful talk.
Thank you.
Okay, at this stage, it is our lightning round. So I'd like to invite our poster presenters up. If you'd like to line up in order, at the bottom here, and I will change the slide. And as soon as your slide comes on stage, you have 1 minute to pitch your poster. I will stand over here. Use the lectern mic. Okay. Are we ready? Are we in order?
Am I using the microphone?
You can use this microphone if you'd like, yeah. Oh, we can use the lectern. Are we on the lectern? Lectern microphone. Lectern. I'll come over here. First round, we're working out the things. Okay.
All right, so my research is all about fat replacement in food, the optimization of lower calorie foods, and also basically making plant proteins a bit nicer to eat, because if you've ever had them, plant protein powders are quite horrible. So essentially what we do is we microgel plant proteins, and basically we create these gel-like, bead-like particles, 100 to 300 nanometers in size. And when we've characterized these using AFM, rheology, adsorption, and tribology done using a 3D biomimetic tongue, we look at the friction values, and we found the friction of these microgelled proteins to be really lubricating, even more so than an oil and water emulsion we made. And so essentially, this microgelation can be applied to plant proteins to make them not only nicer to consume and texture-wise, but they can also be great as a fat replacement in food design.
Thank you very much. Next up, we have James.
Thank you. So my work reports on some early stage work looking at using a self-assembling peptide, glycosaminoglycan hydrogel, to restore the biomechanical properties of patella cartilage, where one characteristic is softened cartilage within chondromalacia patella, which effectively is an early stage precursor to osteoarthritis within the knee. And what we find is that's associated with glycosaminoglycan loss. So the hydrogel is used as a supportive material, and we have assessed that through an in-house gag-depleted model of the patella, and we've used a static indentation model and test to see whether or not we could restore the biomechanical properties of the gag-depleted model from the degenerate stage to the native, and we've actually, early stage, shown that we have restored that to a native-like state.
Wonderful, thank you very much. So next up we have Merrin.
Hi, I'm here to talk about the work I have been doing on blocker polymer phase separation. So blocker polymers are these amazing designer material which can segregate, in which the monomers can segregate together to form different patterns, which can be periodic or aperiodic, depending upon the architecture of chains and also the monomer interactions. And so as I said, they can form periodic as well as aperiodic structures, but they can also form quasi-crystals, which made a revolution in crystallography. So in my work, we use the theoretical framework of strong segregation theory and combine it with the idea of tilings to study, to find the free energy of these phase-separated structures, and hence to find whether there are any stable quasi-crystalline structures in that. To know more about how far we got and how I'm doing it, have a look into my poster or talk to me. Thank you.
Thank you very much. And last but not least, we have Daniel.
Hi, I'm Daniel Baldwin. I'm a PhD researcher in applied mathematics under the supervision of Dr. Steve Fitzgerald. My research is concerned with particle escape rates, the notion of a physical object overcoming an energetic barrier driven by random thermal fluctuations is ubiquitous in the physical sciences. For example, in chemical kinetics, the barrier is known as the activation energy. Now, much of the current literature assumes that the noise, i.e. the surrounding particle bath, is uncorrelated, i.e. it has no memory of its history. But for true physical systems, this can be seen as quite a dramatic oversimplification. The premise of my master's research was to instill exponential time correlations into a system to see how it affects its evolution. There was a brilliant analytic formula derived by a man called McCain. We derived stochastic simulations to check the validity of this formula, and rather surprisingly, the data matched up really well. From this, we want to generalize this notion of instilling memory into a system to look at much more complex scenarios, such as mentioned before, protein folding.
Thank you very much. Brilliant. So if you'd like to thank all of our speakers again who did a wonderful job in the lightning round. If you'd like to know more about their posts or ask any questions, they'll all be available this evening at the drinks reception in the designated in the soft matter session. Sorry, lost my words. Okay, so we are actually running just about on time, which is wonderful. So I'd very much like to invite our next speaker up, Dr. Olivia Pabois. Thank you.
Hi, everybody. I'm part of the team of Anwesha Sarkar at the School of Food Science and Nutrition, and I'm working on Aqualab, a European Research Council proof of concept funded project. And my postdoctoral research work aims at designing, characterizing, and commercializing an innovative aqueous lubricant to be used as a saliva substitute for patients suffering from dry mouth. And my presentation today is focusing on the understanding of the structure-function relationship governing the lubrication properties of our recently developed brand new super lubricious Microgel-reinforced hydrogel. So did you know that 1 in 10 adults suffer from dry mouth as a result of reduced or absent saliva flow, and that this condition, which can be a side effect of cancer-related radiations or polymedication, has a detrimental impact on the ability to chew, swallow, and speak? Later today, you will probably enjoy a nice piece of meat with flavorful veggies, and currently you're probably sitting down to a steaming cup of tea or coffee to tackle the long day lying ahead. But suppose that because of oral dryness, everything you are eating or drinking tasted like paper, dry in texture and bland in flavor. How would you feel? Numerous saliva substitutes are currently available on the market, but none of them offer long-lasting relief. Imagine, therefore, how uncomfortable and embarrassing it must be for a patient to repeatedly use mouth spray all day long to be able to eat or speak. Our objective through Aqualab Sense commercialization project is therefore to design a more efficient and innovative saliva substitute which offers both substantially enhanced and sustained hydration properties. So, human saliva, which is constituted of 99% water, electrolytes, and proteinaceous compounds such as mucin or lactoferrin, plays a key role in oral functioning, not only by providing lubrication to protect oral tissues, but also by promoting food disintegration and swallowing to facilitate food oral processing. And very recently, its remarkable ability to coat and lubricate the mouth, the oral cavity, ultimately reducing frictional damage, has been attributed to a synergistic interaction between electrostatically self-assembling salivary proteins. So briefly, the negatively charged mucin was found to form a water encapsulating mesh, therefore providing hydrodynamic lubrication, whereas the positively charged lactoferrin was found to tether this water reservoir to the surface, therefore providing boundary lubrication. So building upon these fundamental insights and making use of the proven excellent lubrication properties of both microgels and hydrogels, we have recently developed and patented a brand new colloidal formulation, which is composed of a positively charged lactoferrin microgel dispersed in a negatively charged kappa-carrageenan hydrogel. So first of all, we preliminarily characterized its structure, both at the microscale and nanoscale, combining scattering techniques such as small angle neutron and X-ray scattering with transmission electron microscopy. And then we study its lubrication properties by using tribology with dry mouth mimicking surfaces. And finally, we investigated its oral friction reducing effects by assessing both its rheological and interfacial properties with a rheometer and a quartz crystal microbalance. So first of all, we characterize the structure of our colloidal formulation, starting with a structural characterization of each individual component. So transmission electron microscopy images showed that the lactoferrin microgel forms spherical particles, which based on light scattering measurements exhibit a 150 nanometer hydrodynamic diameter, whereas kappa, carrageen, and hydrogel was found to form biopolymeric rod-like chains. And when dispersed in kappa, carrageen, and hydrogel, lactoferrin macrogel particles were found to be embedded in the interconnected network of nanofibrils formed by kappa, carrageen, and hydrogel. So based on these preliminary results, we hypothesized that our colloidal formulation is composed of cross-linked proteinaceous networks forming spherical particles, which are surrounded by a shell of nanofibrils adsorbed on their surface due to electrostatic interaction. And interestingly, our lubricant was found to exhibit a stretchy behavior pretty similar to the one found, pretty similar to the string on the bead phenomenon observed with real human saliva when looking at it under between two fingers. And then we complemented our structural studies by using small angle neutron and X-ray scattering in order to get further insight into the structure of our formulation at the nanoscale. And to do so, we use different solvents such as D2O, H2O, and a mixture of both matching the protein in order to create some contrast in the system and facilitate data analysis. So today I'm just going to show you the results obtained in D2O using small angle neutron scattering. So for now, we have preliminarily fitted our data using a pretty simple model, which is a shape-independent unified fractal model, which is simply described by a radius of gyration and a power law. And the results suggest that the lactoferrin macrogel exhibit a radius of gyration of around 300 angstrom with a power law of around 3, which shows that the lactoferrin macrogel has a globular shape with a rough surface, whereas kappa, carrageen, and hydrogel seems to exhibit a radius of gyration of around 100 angstrom with a power law of around 1.2, which suggests the presence of polymer chains floating around in solution and forming a network. So these preliminary results are in agreement with our assumption that the lactoferrin macrogel form globular or spherical particles, whereas the kappa, carrageen, and hydrogel is composed of biopolymeric rod-like chains. And the analysis of the curve corresponding to their mixture using the same exact model suggests the presence of a less compacted structure, but so far does not allow confirming our assumption that the microgel particles are embedded in the network of nanofibrils formed by kappa, carrageen, and hydrogel. So clearly we still need to do some data analysis. And then we investigated the lubrication performance or properties of our technology by using tribology. So friction, wear, and lubrication occur during the motion of oral surfaces, such as the tongue and palate, and particularly arise during food oral processing. And soft tribology, which allows measuring the friction between two deformable surfaces in contact as a function of their motion, is an essential tool to assess the lubrication properties of ingested food products. So the typical Straber curve obtained with tribology usually shows 3 different regimes, which in the case of oral lubrication studies correspond to 3 different stages of food oral processing and different amounts of food in the mouth. So at high speeds, a large amount of sample is entrained between the 2 surfaces in contact, which here mimic a tongue and palate, and forms a layer which pushes the 2 surfaces apart, therefore reducing friction. So in this hydrodynamic regime, the ability to reduce friction depends on the lubricant viscosity. At low speed, the 2 surfaces are in contact with each other, therefore excluding the sample from the contact area and resulting in high friction coefficients. This boundary regime is strongly influenced by the ability of the lubricant to adsorb onto the substrates. And in between these two regimes is the mixed regime, for which both coating and weighting play a key role in reducing oral friction. So first of all, we conducted tribology measurements by using a mini traction machine with a PDMS, with smooth elastomeric hydrophobic surfaces, which are actually a PDMS ball and a PDMS disc in a sliding rolling motion. So with its modulus close to the one found in the mouth, with its hydrophobicity and with its proven ability to adsorb salivary proteins, PDMS is commonly used in oral lubrication studies to mimic a dry mouth. Our results demonstrate that our technology, which we can see in red on the right graph, drastically reduces the friction between the two surfaces in contact, both in the hydrodynamic and boundary regimes, and performs strikingly better than both individual components and the naturally lubricating human saliva, which we can see in gray. Then additional, more biologically relevant tribology measurements were conducted using a rotational rheometer adapted as a tribological setup in purely sliding condition, in combination with a 3D textured elastomeric surface recently developed in our lab. So this surface replicates the size and spatial distribution of fungiform and filiform papillae, therefore mimicking the hydrophobicity, the roughness and stiffness of the real human tongue surface. Our results confirm that our lubricant, which we can see in red again, exhibit an unprecedented lubrication properties that exceed those of other fluids, including the real human saliva, again shown in gray here. So all these results clearly demonstrate the high potential of our lubricant to work as a saliva substitute for patients suffering from dry mouth. And finally, we investigated the rheological and interfacial properties of our technology to shed light on the structure, the molecular mechanism, of responsible, for the super lubricity of our technology. And viscosity measurements show that our technology, in red again here, exhibit a shear thinning behavior, which is pretty similar to the one found exhibited by kappa-carrageenan and hydrogel, compared to lactoferrin microgel, which is much less viscous. And a quartz crystal microbalance was used in combination with PDMS-coated crystals in order to assess the amount of material adsorbed on a dry mouth mimicking surface. And results demonstrate that, contrary to kappa-carrageenan and hydrogel, whose extent of adsorption remains quite low, our technology readily adsorbs at the interface, similarly to lactoferrin microgel. So this preliminary set of data suggests that the outstanding lubrication properties of our technology are due to a synergistic interaction between the two electrostatically binding components, so the highly viscous kappa-carrageenan hydrogel, which may generate hydrodynamic lubrication, and the efficiently adsorbing lactoferrin microgel, which may generate boundary lubrication. To conclude, our results demonstrate that the interaction between lactoferrin microgel and kappa-carrageenan hydrogel results in the formation of biopolymeric nanofibril coated proteinaceous spherical particles with an outstanding ability to reduce friction. And very recently, the high performance of our technology was confirmed through benchmarking studies, where we compared the friction-reducing effect of our technology, which we can see in red on the right, compared to commercially available products, which are shown here in black. So currently, we are further analyzing our small angle neutron and X-ray data, and soon we will be complementing these studies with cryotransmission, electron microscopy, and molecular dynamic simulations. And in parallel, we are further investigating the friction-reducing effect of our technology using nanotribology and looking at the extensional viscosity of our lubricants. And in addition to better understanding the structure and function of our technology, we are working on testing its commercial feasibility. So after demonstrating the performance, confirming the performance of our lubricant as a saliva substitute in our lab, and after patenting it, we have been working on engaging with a manufacturing partner to develop a prototype, such as a bottle of spray. And we have been conducting some market analysis where, in order to confirm that there were indeed unmet needs for a more efficient product. And soon we will be conducting a customer preference study in order to help for product design, and we will be hiring a regulatory advisor to better understand the regulatory route and the safety requirements, and a commercial expert to help us build a robust business case. And on the longer term, we would like to conduct clinical trials to confirm the real-world efficacy of our lubricant. And we would like also to assess what is the best financial strategy between a technology licensing and spin-out creation. So now I just want to acknowledge the ERC for the proof of concept grant awarded, as well as my supervisors and collaborators for their contribution to the project, and you for your attention.
Lovely, thank you very much, Olivia. Are there any questions for Olivia? Oh, one from Edmund.
So thank you very much. You talked about the problems with the existing products, and you obviously got a new product you're trying to get through. So how much improvement does that have over the existing products in terms of, say, the time between treatment to what you're suggesting, how long it would last?
Yeah,
Do you have an idea for that?
Sorry. From these data, clearly you can see that our technology, which is in red, is providing better lubrication compared to different commercial products which we tested in our lab. And we estimate it to be like 90–95% better lubrication. And currently we're also looking at the longevity of our technology compared to commercial products. Because actually one of the main complaints by patients is that the current products are not providing, as I said, a long-lasting relief. So we will be using the QCMD to look at how long our technology remains attached to the surface. So how long does it stay attached to the palate and the tongue? And we will do the same with commercial products to compare. Yeah, we can.
Thank you. Are there any other questions? Down here at the front, Tom.
Yeah, thank you for just a lovely talk. I know the whole question of saliva mimics has been a big one for the food processing industry for a long, long time. Yeah. But just looking at the rheology, just the diagram at the bottom left there of the famous self-experiment that you can do disgustingly with your own spit. But it's very interesting, you know, different parts of the mouth. You can do that little experiment. It gives you different extensional rheology. Does your product seek to match that extensional rheology property of saliva, or is that not important?
So for now, we just looked at the rotational. We just used the rotational rheometer, where we looked at the viscosity over shearing deformation. And our plan is next to use an extensional rheometer, because, as you know, as you say, it's more relevant. Yeah. So for now, as I said, we just have done like studies with shear deformation. But yeah, that's something we're planning to do, again, like looking at our technology, comparing with saliva, commercial products.
In terms of mouthfeel, it's likely to be. And we came across so many industrial questions when I was here of products that they'd made with identical shear rheology, absolutely identical, yeah, but one was working and one wasn't, and it was always in the extension.
Yeah. Thank you.
Okay. Oh, there's another question over here.
Hi, really interesting talk. When you're doing the Strybeck analysis, what kind of speeds do you expect in the mouth during chewing?
Sorry, I didn't.
When you're talking about tribology, if you go back to the Strybeck curve you had,
yeah.
What kind of speeds were you using to do those tests? Like the kind of speed you expect as you chew?
So what kind of speed you said?
Yeah, during chewing.
We are looking over a range. So I'm showing it's friction over motion, so the speed range. So I don't remember it. So from 0. Well, it depends. So we have two different techniques, as I mentioned. And for instance, for the tribometer, we have a speed range of 0.01 to 1 meter per second. Does it answer your question?
I was just asking how that related to like chewing, if you actually get speeds like that in your mouth. As in like how the loading profile was developed when you did the tribology? Like
orally relevant, you mean? Yeah, relevant maybe. To what? Yeah, I don't know. No, sorry.
Okay, I think that was my question. Thank you.
Thank you. Are there any more questions? Actually, I have one. In your roadmap for commercialization, have you got a time frame associated with that? How far do you think it is until, how many years per se do you think it is until this is in patients' hands or mouths?
Yeah. So we are currently developing a prototype, and we hope it to be done in a few months. And as I said, we'll soon be doing consumer preference studies and looking at the regulatory route. And hopefully this will take a few months, but obviously to reach regulatory approval will take years. And for clinical trials, we still need to find some funding to do that, and we are working on looking for collaborators, things like that. But again, this is going to take, I guess, at least 1 year.
Thank you.
You're welcome.
Okay, well, if you'd like to join me in thanking Olivia again. And with that, we can close our first session.
just have to wait to receive the light. If you dare to receive it. Just have to
Okay, lovely. Right on time. So it gives me great pleasure to introduce Dr. Chiara Ciccarelli to open up our next session, session 2, which is on electronic and photonic materials. Chiara.
And you're next. Good. Okay. Yeah, okay. Yeah, good morning, everyone. It's really nice to be here in Leeds again. I came a few times and already, and that's because we also have some collaborative projects I'm going to tell you a little bit about today. So the aim of today is to give you an overview of the recent research in the group, especially highlighting the links with Leeds. And so let's go straight into it. Before I start, I just want to say that I'm most grateful to the Royal Society and the Winton program, which funded this research. So just to introduce my research, I thought of putting up this slide, which shows the increase in the capacity, data capacity of data centers from 1987 to 2017. I mean, this might not catch you as a surprise, especially if you were born around 1987, as I was. We all know what's going on. We are experiencing an explosion in data traffic. Brought by cloud computing, artificial intelligence, bitcoins, and so on. Now, all this comes with a cost in terms of energy. Just to give you an idea, to keep just bitcoins running, we need as much energy as the whole country of Germany. So the aim of Spintronics now is to find most efficient ways from both the speed and the energy point of view to store and process data information. So we can probably identify 3 keywords around which Spintronics is structured and which also inspire the research, my research in my group, which is non-volatility, speed, and scalability. And obviously all these 3 keywords rotate around green, so energy efficient. Now, non-volatility means magnetism. Magnetism has been one of the first ways which we learned about to store information via the magnetization of nano units, magnetic units, which we associate to different bits, 0 and 1. So this is just one of the first examples of MRAM from the 1950s with the amazing density of 32 kilobits per cubic foot. Now, scalability to me means electricity. So we need to be able to write and read nano scale magnetic bits. And it is much easier to confine electrical currents to this sort of nanoscales with respect to optics, for example. And, and then speed, lately speed means that we need to be able to write and read these magnets as fast, for example, as we make silicon transistors work in order to make these magnetic technologies be as competitive as silicon-based technology and eventually replace it. Okay, so in order to respond to the need of scalability, and non-volatility, a very important thing to us in our group is spin-charge interconversion. So what we want to study is most efficient ways to convert spin information into a charge signal, and vice versa, to use charges, to use electrical currents to manipulate the magnetic orientation of a magnetic bit. Now, there are essentially 2 ways to do that. One is naturally provided to us by the spin-orbit coupling when space inversion symmetry is broken, for example, within the unit cell of a crystal. And we have dedicated many years to this sort of studies, but I'm not going to present this to you today. I'm going to focus on the second method that we have, which is also nicely provided to us by nature, and which is by using an external spin-to-charge transducer, external to the source of spin, which is the magnet. So this spin-to-charge transducer is a heavy metal, a heavy paramagnet, for example, platinum or tantalum. It is not magnetic by itself, but if we flow an electrical current into it, this is the uneven scattering of carriers in spin due to the spin-orbit coupling causes a transverse spin current, which then results in an opposite spin accumulation at opposite sides of at opposite interfaces. Now, vice versa, if we inject a spin current into the paramagnet, this is converted into an electrical current, into a charge signal. Now, the charge current, the spin current, Js, and the spin polarization, sigma, are correlated by this simple relation given by the cross product, so they're all perpendicular to each other. Now, once we have this nice, beautiful spin-to-charge transducer, the only thing we need to worry about is how to transfer spin from the reservoir, from the magnet, into this transducer. And there are mainly two ways used in spintronics. The first one is spin pumping, where the magnetization of the ferromagnet is set into coherent precession. So as the magnetization precesses, it naturally creates a non-equilibrium spin population, which then diffuses towards the platinum, the spin-to-charge transducer, and it is converted into a voltage signal, into a charge signal, which we measure. And the intensity of this voltage tells us immediately how much spin we were able to inject into the platinum, or create and inject. The second method is instead consists in creating a temperature gradient across the interface between the platinum and the ferromagnet. And this temperature gradient naturally induces the drifting of the spin from the ferromagnet into the platinum. And again, we convert through the platinum this spin into a charge signal, into a voltage. Now, because in these two cases, we're basically relying on the excitation of magnetic dynamics. In the first case, coherent magnetic dynamics. In the second case, uncoherent magnetic dynamics. But still, we're basically working at the natural timescales with which magnetic dynamics are excited, which is typically in the microwave. So all these experiments are normally done by using methods that span from the DC up to the microwave. Whereas today I'm going to show you our recent measurements on the spin-Seebeck effect carried at 1,000 times faster timescales. So we're working in the picosecond timescales. Okay, so this project was done in collaboration with Joe Barker, which is a theorist working here in Leeds. Okay, so our background is in spintronics, so as I said, we mostly worked in the microwave range. Now, only more recently, we became very interested in exploring spin effects in condensed matter at faster timescales. So this made us expand our bandwidth into the terahertz range and build a time-resolved optical pump terahertz emission setup, which basically all you need is a femtosecond laser. And then we use this laser to create terahertz monocycle pulses, which we can shine directly on the sample and measure the transmitted signal. Or what we can do, we can pump an optical pulse, a femtosecond, very quick optical pulse on the sample, and then measure the terahertz electrical signal emission that results from it. And that's the layout that we're going to use for this experiment. Now, before we go into the details of the experiment of the fast measurement of the picosecond, of the spin-Seebeck effect, let's have a quick scroll down the main results obtained for the slow measurements of the spin-Seebeck effect. So all these measurements have contributed to depict a coherent picture on the phenomenology and what causes the spin transfer when we create a temperature gradient across a magnet and a heavy metal. Now, most of the studies have focused on a particular magnet, which is YIG, and the reason for that is that YIG is a ferromagnetic dielectric. So in this case, we suppress all contribution from the movement of free carriers of charges. So we can only associate the spin transfer to magnons, which are the quanta of spin excitations, and phonons eventually. So what these results have contributed to show is that the spin transfer is mediated by magnons, or which are also called with a more descriptive name, spin waves. So basically, these magnons obey Bose-Einstein statistics. So as if we increase the temperature, their population increases. So if we have a temperature gradient within the bulk of the ferromagnet, we also create a gradient in their population. So when these magnons then diffuse from the hotter regions to the colder region, they induce a non-equilibrium spin, which then again at the interface with the platinum starts to diffuse towards the platinum, and that's what we need to then generate an electrical signal in the platinum, which we read out. Now, this picture also justifies why we see, as a function of YIG dependence, a saturation and a dropping in the spin-Seebeck effect if we go towards zero thickness of YIG. This is because the magnons have a finite propagation length. So if we have a thickness of YIG which is below this finite propagation length, then obviously we're able to use less of the spin that these magnets can propagate, and the signal drops towards 0. Also, this picture describes well the temperature dependence that we observe in the spin-Seebeck effect, where we see that as we decrease temperature, the signal starts to increase, and this is because the propagation length of magnets increases as we decrease temperature, but then it reaches a peak and then decreases again towards 0 Kelvin. This is because towards 0 Kelvin, these magnets having a Bose-Einstein distribution, obviously the population starts to decrease. And less magnets participate to the transfer of spin. So that's an important result. At 0 Kelvin, we expect a total suppression of the spin-Seebeck effect. Now let's go to our measurements. So in our measurements, we used a very different layout to what normally used in spintronics. What we did, we had YIG platinum, same device as normally started in DC measurements, in slow measurements. We shined a 50 femtosecond optical pulse on the sample. Now, because platinum has a much higher absorption coefficient with respect to YIG, most of the energy from the pump is absorbed by the platinum and heats up the free carriers in platinum. So these free carriers become very hot very rapidly. And because the YIG doesn't have the time, at the fast time scales that we're measuring, doesn't have the time to warm up, we immediately create a very high temperature gradient between the free carriers in platinum and the magnon bath or the phonon bath in YIG. So this creates the temperature gradient that we need for the spin-Seebeck effect. And if any transfer of spin follows up from this temperature gradient, then we will be able again to collect it in the platinum and to convert this impulsive spin transfer in the picosecond range into a picosecond charge current pulse. Now, this current pulse as an antenna will emit electrodipole emission in the terahertz. So what we're measuring in the output is effectively a terahertz pulse. Okay, so we optically pump and measure a terahertz pulse, which intensity is directly proportional to how much spin we have injected into the platinum via this optically induced temperature gradient. Okay, so we have three elements that tell us that what we're measuring is actually the spin-Seebeck effect. The first element is the magnetic field dependence. So the polarization of the spin currents that we inject in the platinum reflects the direction of the magnetization of YIG. So if we flip the direction of the magnetic field, we expect a flipping in the direction of the spin polarization that we inject. And because the charge current, as you see from that cross product, that we create in platinum is directly related to the spin polarization, by flipping the sign of sigma, we flip the sign of JC. And so with the polarity of our terahertz emission changes, and we see that very well. Second evidence, pump direction dependence. So what we're doing here is flipping the sample in two different directions with respect to the optical propagation direction. So by flipping the sample, because the charge pulse is always generated in YIG, so the spin current is always transferred from the YIG to the platinum, by flipping the sample, we are effectively inverting the direction of the spin current, which again follows in a flipping inside of the charge current, and therefore on the polarization of the emitted terahertz signal. And we see that in this bottom graph. The third evidence is the pump polarization dependence. So basically, we're changing the angle of polarization with which the pump pulse is linearly polarized, and see whether there's any effect on the emitted terahertz signal. Now, you need to look at the S minus sign here, which corresponds to the spin-Seebeck component. The other component is something else that we attribute to a different effect. So as you see, the red dots there are completely insensitive to the polarization of angle of the optical pump, which tells us that whatever we're measuring has a thermal origin rather than some associated to some optical effect, for example. Okay, so we're measuring a fast version of the spin-Seebeck effect, and probably the main result of our work is in the temperature dependence of this effect, which, as you see, differently from the slow measurements, in this case we see a continuous rise in the signal, in the magnitude of the spin-Seebeck effect. We don't see any peak structure and then a dropping towards 0 Kelvin. And the reason for that is that in these fast measurements, the magnons that contribute to the spin transfer are not those in thermal equilibrium with the environment. So we're not really affected by a change in ambient temperature. Even if the temperature is 0 Kelvin, we are still exciting these magnons via the hot electrons in platinum. How does this occur? So we said the optical pump arrives, it heats up the free carriers in platinum. Now these free carriers quickly thermalize with a phonon bath within the platinum and reach a semi-Dirac distribution. But then they need to start to thermalize with the YIG. How do they thermalize with the YIG? They can thermalize via two main processes. The first one is direct electron-magnon interaction, and this is quite fast. The second way is via phonons, okay, phonon-mediated processes. But these phonon-mediated processes are rather slow in the 10 to the 100 picosecond range. Our detection measurement is only sensitive to a few picosecond range. So we're really filtering out all the slow mechanisms. So in our measurement, we're effectively only sensitive to the direct electron-magnon processes that create magnons in the YIG. And then these magnons are those responsible for creating a non-equilibrium spin population, which then is injected back into the platinum, and we measure it. So by this measurement, we're effectively measuring the efficiency of this scattering process as a function of temperature, which is parameterized in spintronics with what is called the spin mixing conductance. Now, because, what we expect is that the efficiency of this process of this scattering is also described by the Fermi-Golden rule as any scattering process. So it will depend on the density of states of the magnons, so the states that are available for the magnons to be scattered in. So we also expect that the temperature dependence of this spin-Seebeck effect will also will be affected by the band structure of the magnons in YIG. And that's what we attribute this small change in gradient at about 100 Kelvin to. So at the bottom graph, you see that these are calculations done by Joe Barker on the band structure of magnons in YIG as a function of temperature. At 100 Kelvin, we have just about enough energy. You see that the red bands and the blue bands correspond to two different spin polarizations. So we normally excite magnons at lower energy in this parabolic band. But then at 100 Kelvin, we have just enough energy. Our hot carriers in platinum have just enough energy that are able to excite magnons in these upper bands, flatter bands. And this is what we attribute this change in gradient to. Okay, so this, just to conclude this first part, we have seen that in our method we have, I've shown you a fast measurement of the spin-Seebeck effect. I've shown you that what we're sensitive to is fast processes, so the direct electron-magnons interaction. I've shown you that this leads to a net spin transfer from the YIG into, and a fast spin transfer in the picosecond range from YIG to platinum. Now, this work is following up is branching into two more collaborative projects, again with leads. The first one with Joe Barker, because we said that this scattering process is so sensitive to the band structure of magnons in the magnet. We're now exploring the spin-Seebeck effect in antiferromagnets. So rather than using YIG, we are using an antiferromagnetic electric. And the reason why antiferromagnets are interesting is because they are characterized by the opening of a gap in the density of states in the magnets. So all these magnets at low energy are no longer accessible. And we see a very clear, nice evidence from this opening of the gap in our measurements. And the second project involves instead ferromagnetic metals, not dielectrics. So in this case, we also have a contribution from the free carriers in the metal. This is in collaboration with Chris Marus, again, here in Leeds. And what we're showing here is that also, despite having an important contribution from the free carriers, still the magnons contribution is important. And it is a contribution that is always neglected in other measurements because it's very hard to disentangle from the free carrier contribution. Okay, so in the second part of the talk, we've gone around a little bit this diagram. I want to really go to the core of it, so the green aspect of spintronics, so really trying to lower the energy as much as possible. Now, when we talk about scalability and therefore electricity, obviously we cannot run away from ohmic dissipation, so from all the energy consumption that comes from resistive losses. So our idea, in collaboration with the Department of Materials in Cambridge, was to use materials in which ohmic losses are completely suppressed, and these are superconductors. So can you imagine how good it would be if, for example, we were able to convert a spin information into a superconducting current? So before answering this question, we need to be able to answer another question, which is, are we able even to inject spin into a superconductor? And this is not an obvious question because we know that from the BCS theory of conventional superconductors, below the gap, the superconducting gap, we have singlet Cooper pairs that are in a singlet state, so they have a zero spin, so they cannot carry any spin information with them. But also, if we put a ferromagnet in contact with a superconductor, the exchange field of the ferromagnet wants to align all spins in the same direction, so it really tries to tear apart Cooper pairs, which also has a detrimental effect on the Cooper pair correlation, and therefore closes the superconducting gap at the interface. Now, so in order to have some spin transfer into the superconductor, we need to solve the first issue. So how can we deal with singlet Cooper pairs? We cannot deal with them. We need triplet Cooper pairs. We need spin polarized triplet Cooper pairs. Is this even possible? Doesn't this contradict Pauli's exclusion principle? I mean, Pauli's exclusion principle tells us that the wave function needs to be asymmetric. If we have S-wave superconductor, the spatial function is symmetric, so the spin function must be antisymmetric. But it turns out that if we include time in the correlation, then the symmetry that we actually need to obey is this SPOT equals to -1. So S is the spin part of the wave function. P is the flipping in coordinates of the two electrons in the pair. O is the flipping of the orbitals if they're staying in different orbitals, and which one I'm missing, T is the flipping in the time coordination coordinates. So basically what it means is that the electrons of a pair are completely uncorrelated at the same time, but one electron becomes correlated to the future version of the other member of the pair. So if we take this into account, then we can have an asymmetry. We can have an asymmetry of that kind. So it becomes possible to have, for example, by introducing time inversion asymmetry, so to have T -1, and this satisfies the condition having S equal to 1. So it becomes possible to have a triplet state, S equals to 1, so a symmetric spin function, if we introduce T -1. So if we introduce the break of time symmetry. And the break of time symmetry is introduced exactly by, for example, a ferromagnet, an exchange field, at the interface with a ferromagnet. So by having a superconductor grown in contact with a ferromagnet, we are able to project some of the spin singlet Cooper pairs into a triplet state. But also in this case, the triplet state is not very useful because it's a S0 triplet state. What we need to do is then eventually to rotate this spin 0 triplet state into a spin 1 triplet state. And this is done, for example, by the spin-orbit coupling, by the spin-orbit field. So in summary, we need two ingredients to create spin-polarized Cooper pairs, which we need for spintronic purposes, which is the exchange field, the break of time symmetry, and the spin-orbit field, the spin-orbit coupling. So to show this, we have run a series of spin pumping experiments in different layout structures. So the first one is a structure in which we have a ferromagnet, a permalloy, grown sandwiched between two superconducting layers. We use niobium in this case. What we did was to excite ferromagnetic resonance. So as we said earlier, this precessing magnetization creates a non-equilibrium spin population, which then diffuses away from the ferromagnet into the environment. And in our case, the environment, both at the top and bottom interface, is made by the superconductor. So a very important quantity in our measurements is the line width of the resonance that we measure, because this line width is directly correlated to the how quickly the precessing magnetization is damped. So it's directly correlated to how quickly this precessing magnetization loses angular momentum into the environment. So what we have is that to a wider line width, we expect a higher damping and therefore a most efficient loss of angular momentum into the superconductor. If we have a very narrow line width, what this is telling us is that the ferromagnet doesn't lose virtually any angular momentum into the environment. So the superconductor is repelling the spin. It doesn't want the spin. So this is a measurement of the line width as a function of temperature for different thicknesses of the superconductor. Now this is most clearly seen for the higher thicknesses, so this pink line. As we cross the superconducting transition temperature, this line width drops very rapidly. And this is in agreement with our understanding of conventional superconductors. So above TC, niobium basically behaves as a normal metal. So whatever non-equilibrium spin is created by the precessing magnetization, it diffuses away into the metal. But then as soon as we cross TC and the gap opens in the density of states, then these states, low energy states, are becoming unavailable for the spin to diffuse to. So the quasi-particle states that are above the gap become more and more higher in energy. So this suppress, we said that Cooper pairs in a singlet state cannot carry any spin, so effectively the superconductor cannot take any spin diffusing from the ferromagnet. And this loss is therefore reduced. And this is reflected by the reduction in line width. However, if we now introduce another device structure in which the niobium now, on the other side of the niobium, we put a thin platinum layer, which is, again, a heavy metal, so a metal characterized by high spin-orbit coupling, which provides the second ingredient that we need to create triplet pairs. We have the exchange field at the interface with the ferromagnet, but then we need the spin-orbit field, the spin-orbit coupling at the interface with the platinum. So by having this second ingredient, you see that the temperature dependence of the line width now is different. And for some intermediate thicknesses of niobium, we see an increase below TC in the line width rather than a decrease. So this tells us that in this second device structure, we're all of a sudden able to lose angular momentum spin into the superconductor. Now this, I'll probably skip this one. So now, just one comment. We said if you really pay attention to the structure, you see that the two ingredients that we need to create triplet Cooper pairs are on opposite sides of two opposite interfaces of the niobium. We have the exchange field at the interface with the ferromagnet and the spin-orbit coupling at the interface with the platinum. So in order for these two ingredients to talk to each other, obviously we need to have a thickness for the niobium that is comparable to the coherence length of Cooper pairs. And this is why our effect in increasing line width depends strongly on the thickness of niobium and peaks for a thickness that is comparable to the coherence length of niobium, and then it's suppressed again. But what about bringing these two ingredients to the same interface? How did we do that? We magnetized platinum. Now, platinum is very close to a paramagnetic transition. It's very easy to create an internal magnetic moment. Although it's paramagnetic, it's very easy to create an internal magnetic moment, for example, via exchange coupling with a ferromagnet. So what we did, we grew on the other side of platinum, iron, with the simple intention of creating an exchange field, an internal exchange field in the platinum. So the bottom graph here shows the platinum thickness dependence of the line width. In the case in which we only have platinum, and in the case in which we have a magnetized platinum layer. And these two graphs are pretty different from each other. So in the first case, where we only have platinum, we see that the line width, so the effect of, again, I remind you, so how efficiently we lose angular momentum in the niobium and then in the platinum after the niobium, increases with platinum thickness and saturates at about 4 nanometers, which is due to because of the spin diffusion length in platinum. So this is very well understood from the spintronic point of view and from structures that are also non-superconducting. But in the second case, we see that this trend is different, and we see a peak in the effect when the platinum thickness is actually 1 or 2 nanometers. So for a thinner platinum layer, we are able to completely propagate the effect of the exchange field from the iron throughout the platinum, down to the interface with the niobium, so to bring the exchange field and the spin-orbit coupling at the interface with the niobium, which is what we need to create triplet Cooper pairs. If we have a thicker platinum, then the one in contact with the iron is magnetized, but the one in contact with the niobium remains paramagnetic, and we don't have the same effect. So just to show you an application, a device application of these results, we have used now this principle of spin polarized Cooper pairs for gating spin waves. So instead of using the ferromagnet to excite coherent spin precession, we've used it as a channel to propagate spin waves. And what we have seen is that now these two graphs show the one at the bottom here shows the propagation length of the spin wave in the ferromagnet as a function of temperature above and below Tc when there are not spin polarized triplet pairs. So in the case when we only have singlet Cooper pairs, you see that the spin propagation length is higher at 2 Kelvin, the blue graph, and this is because the spin wave is not able to lose angular momentum in the environment, whereas in the graph at the top, we have triplet spin polarized triplet pairs, and the spin diffusion length is actually decreased. So the spin wave propagation length is actually decreased at 2 Kelvin below the transition temperature, because in this case, the loss of angular momentum is mediated by spin polarized triplet pairs. Now, so just to summarize this, I've shown you that it is possible to inject spin into a superconductor if we have the right conditions. So if we have, for example, spin polarized triplet Cooper pairs. Now, obviously, this is only the first step. Now we need to look into ways to convert the spin that we inject into the superconductor into a superconducting charge signal, for example. And this is just at the beginning. There have been many theory predictions for how this could be achieved. But the experimental side of it is really at the infancy, so it's a really exciting and new field to explore. And also this work has led to a collaboration, an ongoing collaboration with Oscar Cespedes, again here at Leeds, where we are exploring spin pumping into molecular metallic interfaces. He has done amazing preliminary work already showing with muon spin rotation experiments the evidence for the creation of spin polarized triplet pairs in these structures, and now we're doing the same type of spin pumping experiments in this. And with this, I conclude my talk, and I thank you for your attention.
Thank you very much, Chiara. Are there any questions for you, Chiara? Ooh, Edmund.
Chiara, thank you. That's really, really fascinating results there. Can I ask you a slightly more general question, which goes back to your first slide about with the green bit in the middle of it? So we've obviously seen things with some quite complicated structures and superconductors and whatever else. So what do you think are the prospects for that green IT bit in the middle?
Yeah, I mean, personally, I'm biased, but I personally think this area of superconducting spintronic is very intrigued, and because cryogenic computing is still a huge field that is picking up for other reasons. Superconducting logic is offering great opportunities for speed and energy efficiency, but obviously we're missing the memory bit. So this idea of combining magnets with superconductor is very exciting for the energy point of view. And obviously, we will need to guarantee the speed element, and that's also something that is really intriguing us. So really exploring these spin effects in superconductors at timescales that are as fast as the time it takes to break a Cooper pair. So in highly non-equilibrium conditions, how far can we push these boundaries? And that's really the field that we are starting now to explore, and really new physics, really new science, who knows? I'm definitely very intrigued by superconductivity. Mm-hmm.
Thank you.
Great, thank you. Are there any other questions for you, Chiara? One here from Tom. Down here. We'll come to you in a sec.
Just a very quick one, Chiara. Lovely talk. Thank you so much. I expected you to make a differentiation between type 1 and type 2 superconductors in regard to the spin sink nature. Is there any difference?
Well, we need to use type 2. So when we couple to ferromagnets, we need to be able to apply magnetic fields. So we want a superconductor that could sustain these low magnetic fields. And so we prefer to work with type 2
so
superconductors.
Type 2. Okay,
yeah.
you just take it for granted. Thank you. Okay. So type 1 doesn't do anything for you?
I think yeah, it might work. Yeah, type 1 should work, but niobium it can work as well. But obviously you need to deal with fluxes and all this messy bit that we have avoided in niobium.
Thank you. I think there was a question somewhere over here.
Hi, can you please explain how iron is helping in generation of those spin polarized triplets?
So I'm not sure I understood you.
You have shown in a slide that iron layer is helping in forming of spin polarized triplets.
I don't hear well. Did you hear? Sorry.
Sorry. Am I audible now? Can you please explain how iron layer is helping in forming the spin polarized triplets?
Iron?
Yes.
Okay. No, iron is not contributing to create, because these are the two ingredients in a simple form that we need: spin-orbit coupling and exchange field.
No, you have shown iron layer, effect of iron layer.
The iron, yeah. So the idea of having iron on the other side of platinum was to magnetize the platinum.
Okay.
So platinum becomes magnetic, so it develops an internal magnetic moment. So effectively at the interface with the niobium, we have all the two ingredients that we need, which is the exchange field and the spin-orbit coupling. So the idea of iron was basically to bring these two elements together at the same interface. Otherwise they're split. They belong to two different interfaces of the niobium, so they don't talk to each other as well. So
it is for bringing them together. Okay,
yeah,
got
it. Sorry.
Sorry.
Okay, thank you. I think that's all the time we need to move on to the lightning session. So some of you may notice that we're flexing the agenda ever so slightly here. But if you'll join me in thanking Chiara again for a lovely talk. Thank you. Okay, so it's time for our posters again. So our lightning round. So if I can ask our session 2 posters to come up to the stage. Okay, so same rules again. 1 minute and pitch your poster, please. So Alexander first, thank you.
So hi, I'm Alex. I'm working in chemistry as a PhD student at the moment under the supervision of Dr. Robert Menzel. My project is very industrial. It's funded by a company called William Blythe Limited, which are based in Lancashire. And what I'm focusing on is the kind of preparation of these inorganic particle graphene oxide hybrid materials. These materials have a kind of quite a wide range of applications, but some of the ones I'm interested in are kind of energy storage, supercapacitors, rechargeable batteries, as well as photocatalysis as well. And what my poster kind of is looking at today is how understanding the kind of colloidal stability of these particles can be used to synthesize them. And so we did this using a model system of lead double hydroxide particles, which were prepared using an industrially relevant process. And then we went through to assess the experimental stability and the theoretical stability using DLVO theory. So yeah, thank you very much. If you'd like to know a bit more, please come and see my poster.
Lovely, thank you.
Thank you.
Next up, we have Jintao.
Good morning, everyone. My name is Jintao Shuai. I'm honored to present our latest results here, coercivity control of thin films with perpendicular magnetic anisotropy by surface acoustic waves. In this project, we apply surface acoustic waves to different materials to understand the effect of SAW on magnetic behavior of the material. This project is an interdisciplinary study, which includes material science, electronic engineering and spintronics. And we also conduct our study with macromagnetic simulations. So the results show that by applying SAL, one can reduce the coercivity of platinum, cobalt, iridium thin films by up to 18%. Domain patterns with the spacing of half wavelength of SAL can be observed. And the simulation results show that this is because the antinodes of the standing SAL favors the magnetization reversal. And this study indicates the possibility of remote and energy-efficient control of magnetization switching. I'm more than happy to answer your question during the poster session. Thank you very much.
Thank you very much. Next up, we have Lynn.
Hi, my name is Lynn. I'm from the Condensed Matter Physics group in the University of Leeds, and my topic of my poster is about the spectral motion of the skyrmions driven by the spin wave in different width of the tracks and different damping constants. With a larger width of the track, the opposite direction displacement of the skyrmions is more significant, and the motion of a skyrmion is mostly based on the momentum transfer from the reflected or transmitted spin wave. If you would like to get more details, welcome to talk with me in the poster sections. Thank you.
Lovely. Thank you very much. Next up, we have Benz.
Hello, everyone. My name is Benze. I'm based across School of Chemistry and, to a lesser extent, the IPRD. The aim of my project is to create a catalytic water purification system that is capable of both the generation and activation of hydrogen peroxide, which basically means that I want to be able to generate reactive oxygen species for the removal of organic pollutants in water. You can see a diagram in the upper right corner, which is quite a standard for this field, where we use a dye degradation reaction and look at the change in dye concentration versus time. But with my poster, I will try to convince you that this is not good enough for the assessment of catalytic activity of these systems if they are ever to be applied for real-life settings, which the aim of this research should be. So thank you for your attention.
Thank you very much. And last but not least, we have Robert.
Hello everyone, I'm a second year Bragg PhD student and I work in the Condensed Matter Physics group under Dr. Joseph Barker and Professor Steve Fitzgerald. We are rapidly approaching the end of applicability of Moore's law as far as the speed of electronics and the density of data storage that is available. So we are moving towards a spintronics focused research, and we aim to explore the applicability of the strain coupling and antiferromagnets to explain domain formation in these materials. Domain formation in the materials has been observed experimentally in the literature, but as of yet has not been explained satisfactorily, because in ferromagnets it's explained by a magnetostatic energy minimization, but in antiferromagnets this is clearly not the case. So this project aims to create a software package that explores this effect. Thanks everyone for your time.
Thank you very much. If you'd like to join me in thanking all of our poster presenters, they're all available again in the session this evening during the poster session, the drinks reception, sorry. So in a slight change to the agenda, unfortunately, Sean couldn't be with us today, so it's kind of understandable to be able to flex our agenda a little bit, so we have a bit of a ad hoc break for a bit more discussion now, and then we're going to rejoin our next session very shortly. Okay, hello everyone again. So it's my pleasure to introduce Dr. Joe Foster, who's going to take us through into session 3 on Bionanotechnology.
Terrific. Thank you very much. And thank you, everybody. As Andy said, my name is Jo Foster, and I'm from a charity called the Institute for Research in Schools. And actually listening, fascinated to all the talks here this morning, I feel a little bit like an imposter, because I think that this talk is going to be the only talk where I'm not going to present lots and lots of absolutely fantastic research and some amazing new things. But what I want to do is talk about why it's so important that if we want this incredibly vibrant community of researchers as we go into the future, that we have to start with students in school. Now, when I titled this talk, I thought afterwards I probably should have called it, instead of how to turn teenagers into research scientists, I perhaps should have called it how to turn teenagers back into research scientists. Because those of you who either have children or were children, so I guess that's all of us, will know that when you are a child, you really are a scientist. So by that I mean, what happens when I put this in here? What happens when I drop this off there? What happens when I smash these things into each other? What happens when I tip all my mum's best bath stuff down the toilet and then flush it? All of those sorts of questions that as a child, you naturally are really, really curious to answer. As an adult, as we go through school, we kind of have it sort of ground out of us that if we ask why too often, adults will get a bit fed up with us. But I think what happens is some young people get the bug, hang on to it, are tenacious and become researchers. And that's what we're trying to do as a charity, is get young people back into that, why does this happen, that curiosity and excitement of science. So our mission as a charity, and you'll see in a minute we work across the whole of the UK, is to change the culture in UK education. So what we want is we want every young person in the UK to have the opportunity to do some real research. So our argument, my argument, is that when we do science with young people, teaching young people science without letting them actually do real research, and by real research, I mean something where they're going to find something new, is a bit like teaching them to play football, but never ever letting them play a match. It's like teaching them the rules and making them do drills, you know, run back and forward, maybe even copy some other special moves from matches. For some of you, those things will feel familiar from your science lessons, maybe. You know, looking at what other people have done, put A into B, write down what happens, and if you don't get the right answer, well, get your answer from somebody else. You all know that's not how real research works. And we're teaching our young people that that's what research is, and that doesn't seem very interesting. What real research is the creativity, the excitement, the playing the football match. And sometimes if you allow a young person to play that match, they score a championship-winning goal. And that's what we hope that some of the young people that we work with will do. So a little bit about our organisation, and the reason that I'm here today, and I'll come on to it in a minute, is because we've been doing a project with Andy and with the Bragg Centre, and I wanted to tell you a little bit about that. But basically, this is about our organisation, and in part, this talk is a shameless plug to try and get some of you who are watching interested in maybe working with some of our young people too. So if you would like to encourage more young people into research, this is an opportunity for you to get in touch with me, with our organisation, and put that into practice. Basically, we've had over 350 schools join ours since we began in 2016. This year, well, when I wrote these slides about 4 days ago, we had 1,120 young people. That number has now gone up to nearly 1,200. Those young people are in secondary schools in the UK, taking part in real research, often linked or always linked, very nearly always linked to either a university, an academic, or an industry. So real research linked up to real scientists. Questioning the teachers that are involved in the projects, 97% said that the students were more engaged and motivated once they'd taken part in our projects. Now, if any of you have ever done any teaching, you'll know that that is a real win. So I was a teacher for 20 years before I joined IRIS. To have 97% of your class more enthusiastic is an absolute win. So we hope that this is a really helpful thing for teachers too. The students that we work with tend to already be fairly keen on science, otherwise they probably wouldn't choose to do this as an extra activity. What students have told us is once they've done these projects, they're even more sure whether it is for them, because they feel as though this gives them a real insight into what scientists really spend their time doing. And we've got over 80 institutions involved in IRIS projects at the moment. 133 research projects running, some big projects, some pilot projects, some very small. So there might be a student who's really interested in a particular thing, who does an original research project, and we support them and we help them. Sometimes students submit papers for publications, we help them through their research. And as you can see, 3 out of 5 of them felt they knew more about science careers after they'd worked with us. We also have a conference, so probably all of you will feel that presenting at something like this is really helpful in terms of your professional development and sharing your work, and we do the same with IRIS students, and we had over 1,000 visits to. We had a virtual conference last year, lots of students there presenting. So the project I want to talk about today is called the DNA origami pilot. Now, some of you will be familiar with the DNA origami project. This was a collaboration between the Institute for Research in Schools, my organisation, and the Bragg Centre, and very generously funded by the Henry Royce Institute. So enormous thanks to the Bragg Centre and to Henry Royce for this project, where basically we had 55 students from state schools in the UK, of whom you can see 53% knew nothing about material science, and 61% knew nothing at all about DNA nanotechnology. So these young people, not aware of one of the, certainly after today, I feel is probably one of the most important fields of science as we move forward. You know, we need to do something about this, and this is one of the things that we're doing to address that. So. Obviously, we're all scientists here, and these outcomes are not numerical, and that's because the pilot is not yet finished. So yesterday we had and lots of these students here, and we did some final evaluations with them. So the final evaluation results are yet to come. But I can tell you that from this group of young people who worked with us, 2 of them have used their work with DNA origami in their interviews for Cambridge University. In fact, they hear today whether they've been offered places or not. So we know it has an impact in terms of confidence, in terms of opportunity. We also know that a couple of students have now decided to apply to Leeds University on the back of being involved in the project. So really exciting, life-changing outcomes. As you can see here, the students actually made their own DNA origami, which was sent up here, and Andy very, very kindly now, hang on, imaged with the, don't tell me, atomic force microscope. Okay, good. Like a record player, but don't say that because no one knows what a record player is anymore. Okay, so, and they managed to create smiley faces, which when I got the email with the photograph of the smiley faces on, gave me goosebumps. It was one of those moments I just thought, wow, amazing experience for the young people. And then the young people are asked to present their outcomes of their project as a poster. So this is an example of one of the posters that's been produced by one of the groups in the pilot. Now, obviously, you can't read exactly what that poster says, but what this young person did was he took the idea of DNA origami and how it works, and he put his own twist on it, no pun intended, looking at the relative strength of staples and how staples can be more or less stable depending on how you put them into the origami shape. So I just wanted to show this to give you an idea that these are not, you know, take a piece of poster paper and stick some graph paper on. These are really significant pieces of work for these young people. And although in this particular one, you know, we haven't had any breakthrough science well, it is breakthrough science, but you know, we haven't had someone discover or create something incredibly new. We often do in our project. So we had some real excitement last year. One of our projects is using, it's called Earth observation. So the students use satellite images. They can access satellite images, and they can do all sorts of research on them. And this group of students from a school in Scotland, Stirling High School in Scotland, looked at images of the Antarctica and found that if they put a particular filter over the images, they could see patches of penguin guano or penguin poo. Now, of course, you find patches of penguin poo where there are lots of penguins, and they found some patches of penguin poo where there were not colonies of penguins noted. So they got in touch with the British Antarctic Survey and spoke to them, and it turned out they had found some new colonies. Now, that is something that these children did when they were 15 years old. And I think that sort of thing, it can change your view of science, of research, of what you can do forever. And I suspect that most of you will have had a moment or a teacher or a project that has made a big difference to you, and we feel like this work does the same for students. So this is what the teachers said. They enjoyed doing the project, and actually subsequent to this we've done some more teacher surveys, and a third of the teachers that we work with say that getting involved in real research like this with their students makes them more likely to stay in the profession. As you'll know, we need more teachers. We want teachers to be happy and stay in the profession, so we think this is really useful. I'm also really interested in what the students say. I love this bottom comment because it just feels like, there's not many 16-year-olds who would talk about structure and stapling and stable DNA origami. I love it that they're thinking in those terms. But my absolute favorite quote is this one. And I've felt like that about all the talks that I've heard today, like sci-fi movies in real life. I mean, the work that you guys are doing is absolutely fantastic. I think being able to introduce young people to that work while they're still in school and they can see where it can go is really, really important. So we're keen as an organisation to bring more research into schools, to do more with young people, to introduce them to a really diverse range of scientists and researchers so that they can understand what scientists and researchers do. So if you would like to be involved, well, I'm going to be around for the rest of the day. I'll also be here for the event afterwards. I've got our impact report if you want to find out a bit more about our organisation. We believe that this is the way to become a science superpower, to get these researchers in place, is to introduce young people to this in school. Let them play a game of football. Science is creative, science is fun. It's not just doing drills. So please do get in touch with me if you would like to find out a bit more. And that's me done. Thank you very much.
Thank you, Jo. I can say firsthand that working with Jo and Iris is a lot of fun, and it's something well worth doing. And as Jo says, if you want to get in contact to do a project with Jo, then actually through the Bragg Centre, we are having an ongoing relationship with Iris. So the DNA origami project has finished its pilot, sorry, my words are disappearing today. It's finished its pilot, but it's now rolling out again this year and the following year full scale. So I believe this year we've got 120 students
Over
on board.
120 this year,
yeah.
And it will be a lot more next year.
Yeah. So these things scale up and get more and more exciting. So the project will run for those 2 years now, and then after that, we'd very much like to get another project from the Bragg Centre going on a different materials science subject. So any volunteers will be looking for you in the future. So are there any questions for Jo? Tom? Yeah, there's one just there, actually. We'll come back to you.
Hi, Jo. Fascinating presentation and projects. So well done, everyone. But I just wanted to ask, how do you choose the schools? Do you choose it locally? Do you choose the widening participation? How do you choose the schools that participate in the project?
That's a really great question. So we actually are very keen on giving these opportunities to young people who wouldn't have them otherwise. We know that some very successful schools, both state and independent, are very, very good at networking on behalf of their young people, at arranging work experience and putting them in touch with scientists and people in industry. So basically, the simplest answer to your question is the schools can self-select. So state schools can say we'd like to become a member, but we also invite schools, and particularly deprived areas or areas which perhaps aren't well represented with opportunities. We've got 3 target areas this year. We've invited schools to join. We give them additional free support. So we're very much trying to, with a widening participation agenda, make sure that we're reaching those young people who are, perhaps have the least of these sorts of opportunities at the moment.
Thanks, Joe. Fantastic, as always. I've got two quick questions, if I may. The first is I was really interested in your comment that you tend to appeal mostly to the pupils who are already quite excited about science. Which is great, and then you boost them even higher. I'm wondering about whether Iris, maybe that's your field and that's it, that's what you're going to do. But I'm wondering about reaching the hinterland of slightly disaffected ones. Are there any way in which Iris can do that? Maybe by making second visits. So you said no first time, but now all your friends got really excited by this, and the really cool people do really cool things. Could you move into that collection of not yet persuaded people? The other thing, briefly, is you articulated the comparison with football. Do you, as part of an Iris project, are there any points in which you sit the pupils down and you talk about the difference between creative, innovative science and purely science learning, and how the role of imagination in science, and just have a bit of a workshop on what different skills you need for, as it were, the night science as well as the day science?
Okay, thanks very much, Tom. I'll take those questions in turn. So first of all, well, I'll take the last question first, if I may. So actually, we are just about to start a piece of work with some researchers from UCL about looking at how discussion, how talking about what we're doing and why it might feel a bit different to what they might do in everyday science lessons, how that impacts on the young people. So actually, at the moment, it feels almost like at the end of the project, the young people tell us, gosh, it felt really different, it felt really creative. But we don't sort of plant that at the beginning at the moment. But I think there's a great value in starting those conversations. And your second question, which is, well, your first question, which I'll take second, about what do we do about, you said the hinterland, the young people who perhaps don't know that they would be, fantastic researchers, and at the moment are part of what I consider the lost talent pool. So these are the young people who would be incredible researchers, tenacious, interested, curious, but at the moment maybe their curiosity is not directed towards what we would see as, standard science, but in fact, I don't know, can they block the drain before the teacher comes back, and those sorts of creative activities. Now, one of the things that we're really, really keen on, and actually we're about to launch, is a framework to support schools right from year 7 to encourage young people to be involved in research and innovation. So this is the opportunity, starting small for everybody, to experience some of the other amazing things on offer, for example, Royal Society Partnership Grants, the work of the British Science Association, the CREST Awards. You'll all have heard of lots of opportunities, the Ogden Trust, and there are lots and lots of ways that young people can get involved in science. And I think IRIS in particular, IRIS projects are aimed at usually young people who might have chosen or might be about to choose sciences. The sort of project that we talked about today, DNA origami, it's mostly for students who are perhaps 16, 17. And by that time, they tend to have made their choices. Now, we had an art student, didn't we, join us for DNA origami. It's not just science students who it's open for. But we very much recognise that in order to really release the talent that we've got, we need to work with young people who might not think that science is for them, but it absolutely is. And it's because they don't see science in the same way that we do, because at the moment, we don't let them see it that way. But doing real research, we think, lets them see it that way.
Very exciting. Thank you.
Thank you.
Oh, some more questions. Let's go down the front and then to the back.
It's just a question, really. I mean, science and engineering, the practical aspect of it is actually quite expensive for schools and even universities, So, and how can we sort of advocate for more to preserve that in schools and to preserve that in universities? Because I think that's a key aspect of this excitement, really.
Yes. So thank you. That's another great question. So for this project, for DNA origami, we were very fortunate, as I mentioned, that we had support from Henry Royce, and we, I don't know who did it, I suspect the person might be here, somebody put together amazing packs which got posted out to schools. You didn't do it yourself, did you, Andy? Okay, Andy did that. So, and the schools were micro-pipetting and having access to the sort of equipment that actually often, particularly in the less advantaged schools, they don't have. We bought some centrifuges which got moved around the country by my colleague Neil, who's at the back there, who's done an incredible job with the project. But you're absolutely right. Access to sort of cutting-edge practical equipment is difficult in a lot of schools. One of the ways that we overcome this is by partnering with academia and industry. The other way that we overcome it is by getting sponsorship and moving things around so that schools have access. But the third way is that not all our projects, in fact, the majority of our projects don't involve a practical element. Now, I know that a lot of the work here does involve a practical element, but for example, we have coming up a big data project in collaboration with Professor Barr. And that project, the students get access to data from the Atlas project at CERN. So that's very much sort of computer-based and data-based. And we have a number of projects like that because big data is an area which we really hope to, for students to sort of grow into. But you're absolutely right. We would hate to further disadvantage schools by suggesting a project where they can't get the equipment. So wherever possible, we do support with that.
Yeah, I hasten to add that in order to facilitate the DNA origami project this time, we couldn't actually afford to facilitate each of the students coming up with their own design and then paying for that design because that's about £1,000 each time. So they creatively they basically did the computer aspect and the simulation, the modeling aspect of designing the structures to the creative portion, and they then synthesized and purified and made a set structure which we'd previously designed. It's very scalable, but not affordable to do different things. So it fully plays into what you're saying, Rick. And I would like to say that it was we were very much supported by the bioelectronics group as well to facilitate putting out these packages, who will then help us scale that up in the future. So I don't want to do a disservice to the efforts of the PhD students who ran many things around for me while I was not on site. So apologies. I think there were a couple more questions, and then we need to head to lightning talks.
So very interesting. Probably in the same vein, what is it that you look for in a project? I mean, are there any things which are off limits? Any things which work well? Or
yes. Okay. So one of the key things is. It's going to perhaps sound a bit silly, but it's the elevator pitch. Can I understand? Actually, I'm a pretty good barometer. I have got a research background, but disco ball effect. You know, some projects. So, for example, a project called DNA Origami just sounds epic, just because of its name. We've got a project hopefully coming up called Huge Primes, and I can understand, quite easily why those numbers are so important. So what we look for is something which is beyond the curriculum, but perhaps contains a kernel of something that young people will have come across. So it's absolutely academically stretching. We look for a project where we have support from the researcher and hopefully the wider team, because it's enormously motivating for the young people to meet, for example, PhD students who are just maybe 5 years ahead of them, but have got involved in research. We look for a project where it can be usually it can be done within sort of a year. So there's a background information section, then there's the doing the actual practical work, and then there's presenting it. Some schools will run projects over much longer, so they'll take the same project and run it over 3 or 4 years, but most are doable within about a year. And we do look for projects which are real problems in the real world. So a good example of a popular project which is coming to an end now is genome decoders, where we worked with Sanger to help young people to decode the genome, or at least help to decode the genome of the human whipworm, to look for areas which might be useful as targets for drugs against it. So immediately young people can see, okay, this feels like it's important and useful. And I think of all the talks that I've heard today, any one of them could be turned into that sort of thing. All of those things are important and useful. Does that answer the question? Great, thank you.
Thank you very much. I think we're going to have to move on now to keep to time, but Joe is around all day, and any connections with Iris can be made through the Bragg Centre. So, as I said, they'll be seeking further projects in the future with us. So I'd like to, at this point, invite our lightning talks to line up for this session, please. Oh, and of course, sorry, thank Joe. So up first we have Joanna.
Hi, so I've been looking at ferritin, which is a protein code for storing iron. Iron is toxic, but all organisms contain this protein in order to store the ions safely, and this is within the protein cage. There is a core that forms, and we wanted to look at the early stages of the mineral formation. So we took an empty protein cage and added either 3 or 6 ions per cage, which is per monomer, which is about 72 or 144 per cage, and then made the thin layer of ice, plunge froze this to vitrify it. Then we could look at it with cryo-TEM. From the cryo-TEM images, which there's hundreds, we can pick hundreds of thousands of particles, which are then sorted into classifications, which we can then use to build these 3D models. The novelty here is that previous work has used the octahedral symmetry of the cage, which smears out this mineral information across the entire internal surface, whereas we've used a novel workflow which allows us to reconstruct those nascent mineral particles as they're forming. The next stage is to take the data, refine it, and fit a protein model to it so we can actually look at the mineral-protein interactions, and in the future extend this to other materials-protein interfaces.
Thank you very much. Up next we have Ela.
Hi everyone. The focus of my work is to find proteins able to affect the freezing process or ice crystallization using Affimer as model proteins for this study. Inactive proteins that affect ice crystallization are able to bind to ice in the first place. So we start screening many different Affimers against an ice surface in order to identify the strongest binders. And then we analyze their sequences and we test them in a solution in order to see if they show any antifreeze or ice nucleating behavior. So if are able to inhibit or promote ice formation. And we saw that some of the proteins we selected show ice nucleation activity. So thanks for listening. And my poster is the number 13 if you have any other question.
Thank you very much. Next up we have Sam.
My wish is to develop a label-free method for detection and discrimination of functional nanoparticles at the single entity level. And solid-state nanopore is one method that can allow such measurements where the translocation of individual particles results in a specific ionic current signal that we can further use for characterizing them. However, in practice, this method relies heavily on tuning the pore size closely to match the size of the analyte in order to increase your detection capability. And therefore, it limits the study of more complex or heterogeneous samples. In my recent work, I developed approaches that can enhance this detection up to the point of making the invisible visible at the lower nanoscale. Now think about the nanoparticle synthesis sample you want to analyze, or that complex mixture. Or think about the discussion with your in-laws at dinner. They really want to know what weird particles in that COVID vaccine, right? So for all these questions and how, come to my poster 14 and we can talk and have a drink. Thank you.
Thank you. And last but not least, we have Kwan.
Hello, my name is Kwan. Good afternoon. I'm a PhD student in food science and nutrition. We are studying about the water immersion with microgel particle. So the reason why I studied about this is just there are so many products with immersion system including fat, but they are high calorie. So but these days many people want to be good shape. But so imagine if we have the immersion system product without fat, it would be very healthy and just worthy to invest money and time and effort. So we tried to make the water immersion system with particle. So we made water drumlet in specific concentration by starch and kappa-carnitine. So, but it was unstable, so we added to microgel particle. So after that, just they were stable. And when eating some food, oily food, we can feel smooth, oily, and creamy. So they can lower friction in our mouth swallowing food. So the result also show the lower friction coefficient. So it would be very helpful to understand our fat, finding the lead fat replacement in our future. So thank you so much.
Thank you very much. And a reminder that we can see all the posters in the session this afternoon with drinks. So to round off our session, I'd like to invite Dr. Matteo Castronovo to the stage. So, clicker, there's a laser as well if you want. Thanks. Thank you.
All right. Hello, everybody. So today's talk would be about some recent finding about how enzymatic reactions work over DNA nanostructures. So the key problem is understanding how we could manipulate nanostructures made of DNA, not only forming them or characterizing. So from the previous talk Chiara gave, so it's quite clear that the information storage capacity is a real global challenge. And there is a large community of people that believe that DNA could be a next generation material for solving these crises. And if you think about just the capability of containing information and the density of information that can be stored in a device, DNA allows to pack an unbelievable amount of information in a small space because of its natural capacity of storing information. DNA in our bodies stores information for building up a body. So, however, big problem with these type of technologies that if you make some rough calculation, you think about, here we have like the idea is that 200 petabytes could be stored in a gram. Okay, 200 petabytes is about 1/5 of the information that the world produces in a single day. So we need 5 grams of DNA to store information of the world's producing a day. But think about 1 gram. And let's say, about 1,000 base long DNA files, just could be roughly speaking what DNA could be now. It takes about 10 to the 18 unique molecules to store that information. That would be, if you think about making an experiment with Joe or Andy about storing and producing DNA, imagine you are so smart that you can synthesize each molecule, each 1,000 base long molecule in a single microliter. This is really science fiction, but imagine you can do it. If you succeed in doing it, all this amount of information is a lake of a cubic kilometer. So it's really, really difficult to imagine you have facilities and the ability to manipulate such a large amount of volume. So essentially, what we are doing in DNA nanotechnology or DNA in the DNA community is that we are really fighting to create some very functional equivalent of a floppy disk rather than competing with these very modern technologies. So our capacity, real capacity, is probably somewhere here. Okay. However, one very promising approach to compress increase the density that we can use, the density of information in DNA is shown by recent works. One in particular, given by Professor Sayes and the University of Washington, involves the generation of DNA files, so small molecules, let's say a few hundred bases long, that store information, and they are subsequently aligned in the same molecule. So they are ligated one after the other to form a single long molecule that can be then read through a DNA nanopore, a biological nanopore that can actually detect single bases in the sequence. This way, there's a form of compression that allows them to pack a megabyte file in a single solution, in a single set of molecules they generate. However, the reactions that are used to achieve this is DNA ligation, which is quite essential in cloning, but has never been developed to exceed the volume of a single test tube. So what we are using here is technologies that are being developed in molecular biology and have never been somehow compacted or adapted to smaller scales. So this is really what we aim to show today using DNA nanotechnology, a field that was introduced in the early 80s by Professor Ned Seaman, who passed away recently, unfortunately. And there was a boost in discovery, let's say, in the field in 2006 by Paul Rotman at Caltech, where he showed that you can actually form structures very efficiently by involving 2 types of molecules. A long one that is, let's say, a few kilobase long, a circular or linear molecule, and several short DNA stapled, so-called molecules that are involved during a thermal annealing process to fold the long molecule into a smaller compact shape by recognizing non-consecutive regions of the scaffold sequence. So by compacting the molecule, you can create shapes of different types. And in our study, we use a very basic shape, a triangular DNA origami that was actually introduced by Paul Rotman over a decade ago, and nearly 2 decades. And adapting these to study one key question: how DNA ligase, T4, which is a very popular enzyme, recently also characterized at the structural level very recently, how that enzyme works on a structure where the DNA is quite compact. You can see that the space that is required for this enzyme to accommodate around the DNA is quite a lot, or in general, it could be bigger than the space actually available in this very dense arrangement of DNA segments. So what we did is actually tackling the problem from the very molecular perspective. So we have several staples and a scaffold forming the DNA triangle, and we adapted our experimental setup to investigate how ligation works by creating some consecutive ligation events. So we have some ligation, some phosphorylation here, that actually we can provide a continuous different outputs for ligation, like a lack of ligation of one spot here, or full ligation of the complex. Then we essentially melt the structure, we extract all of the components, and then using some subsequent ligation process, we can basically fish each and every component involving the first staple, and then we can characterize them with gel electrophoresis. So the E2 probability of ligating 3 staples together should be, or could be, just the probability of ligating 1 times the second times the third. And this is a quite an important concept that we will discover is not going to work in our origami. So by studying how the ligation works, performs in different locations, by generating many variants of the DNA triangle, we investigated how in different positions of the structure we have, what is the performance, the efficiency of DNA ligation in acting in different locations. So, and we can see from this gel, essential concept is that the different products that we can generate is not equally distributed. So we certainly see also that the efficiency, the total product that is produced by the T4, the action of the T4 DNA ligase is actually varying very much. So we go from 0.2, 0.1 to nearly 2.5 in arbitrary units. So you see here, below 0.1 to 2.5. No, sorry, from below 0.1 to about 0.5 here. So it's quite, let's say, about 10-fold change in the efficiency of the enzyme, meaning that the location, the structural, possibly structural features of the DNA origami are very, very much affecting DNA ligation. So that indicated we need to characterize better how ligation, what are the drivers, the determinants of these reactions. So in particular, whether we made sure that our reactions is endpoint. One key aspect is, have we left enzyme reaction go for enough time? Did we have sufficient concentrations? Of course, all these determinants are quite natural in a reaction. So, of course, we utilize conditions where we are fully saturated. So our reaction is saturated against enzyme concentration or DNA concentration. So basically, we have enough DNA, enough enzyme to make sure that the reaction cannot be improved beyond the limit of what we find. And in the second attempt, we characterize one particular segment, one particular grid of ligation reaction, which is called grid 7. And then here is we have 4 different molecules that can be ligated together, actually in that particular case, with a number of different outputs. And again, the E2 probability of ligating the longest molecule should be, could be, or ideally is just the probability of ligating the first pair of staples, then times the probability of ligating the second pair of staples, and the third. And now then investigated this reaction by gel electrophoresis, where now the ligation reaction is directly visible in the gel because we have fluorescent dyes in the first molecule that is ligated here. And the different products have, so they have an output more or less like this. We generated then variants of the triangle by exploring different defective structures, like having the full triangle or the one missing some staples. You're creating a hole, having a hole on the other side, holes on 2 sides, some missing staples that make the origami components more flexible, or we removed one trapezoid of the DNA origami, one edge of it or the other, or just having a smaller unit to form in the only structure, so just one trapezoid. So by studying all of these different variants, we see here that essentially the good news is that all of them form, also we have atomic force microscopy analysis that confirms the formation of the structures, but most importantly, we see that they perform in a similar way. So in each structure, we have outputs of just ligating 2 staples, then 3 staples, and 4 staples. And what we see here is that some defective structures, those in particular here, are creating different patterns. So we see that the intensity of these bands tend to change quite a lot. And if you measure the intensity of the band's intensity in the gel, we see that a first cohort of changes don't really affect significantly the structure, the reactivity. So we have in log scale that the performance of ligating just 1 pair, 2 pairs, two pairs together, and one staple, 2 staples together, 3 staples, and 4 staples together is as expected. They are showing that there is a 2 probability that we expected is more or less reasonable. So the probability of ligating 3 consecutive staples is certainly lower than ligating 1. But what we find is once we enhance these defects, and in particular we go for a very small units, what we find is that the probability of ligating 3 staples is completely, really diminished. So the ligation reaction is essentially suppressed in a structure that is somehow smaller than the full triangle. Interestingly, however, the total ligation product doesn't change much. You see that the total ligation product here is, for the different structures, is more or less the same. So there is no big changes in the log scale you can imagine. So something that is really close. So we go from 0.7 to about 0.9. So the enzyme actually works equally well in each structure variant, but the ability to ligate consecutive staples changes significantly. Now, we therefore designed another type of module. So we took a crop element of the DNA triangle, and we synthesized that by using 3 different short scaffolds and a limited set of staples, and we reproduced the same ligation cassette in a smaller system. So we compared before what we did in the triangle with what we do here with the smaller unit, the cropped DNA tile, and what we find here is incredibly unexpected in a sense. So what we found is that the efficiency of ligation for the full products, the element containing the 3 staples altogether, is way higher than the one we had in the elements. So basically here, clearly the behavior, the intensity product for L1, which is just 1 ligation event, a 2 ligation event, or 3, is not essentially showing a correlation of ligation. So we suppress significantly the amount of unligated first staples, and we produce an early saturation for the full ligation pattern. Again, here, the full ligation product doesn't change significantly, meaning that the enzyme overall performs equally well in all of these structures. So what happens is, in our previous studies, we characterize how endonucleases work in DNA nanostructures, like basically enzymes that are capable of cutting DNA. And we found that essentially there is a local dependency. So the local structure in the DNA origami can affect the way enzymes can bind to the structure. In particular, we have the rule, let's say a very rough, depiction of this process involves the distance between the DNA strands. So the larger is this cell that we can see, the more the space you can have around DNA, and the more enzyme, and easier is the enzyme access to the DNA. While if you have a smaller distance between DNA, essentially enzymes cannot really accommodate properly. And we correlate the experimental data with the computational results, showing a good correlation. So essentially, using this very simple model, just assuming that big distances allow more access, so smaller distances inhibit enzyme access, is quite a good estimate. It gives you a good rationalization of the process. So in our experiments, however, here with DNA ligation, and this is the last slide, essentially we have a dependency of the total of the ligation product, of the total ligation product, on smaller changes. So we see that the local structure changes, so by changing the position in the structure, leads to significant changes in the performance. So there's something more. Ligation is a bit more complicated than endonuclease, than cutting DNA. But most importantly, once we vary the global shape of the structure, we can see a very large variation in the correlation by which the enzyme works. The way to rationalize, we don't have a model, we don't have access to computational approaches to simulate the diffusion, the movement, the action of enzymes over nanostructures. But our interpretation our empirical interpretation is that if you think about a small system like a larger system like the tetrapeptoid here compared to the crop tile, so our assumption is that the DNA ligase performs one-dimensional diffusion that essentially involves, basically is the dominant component and makes essentially or induces somehow helps the enzyme moving along the DNA, which is some process that the DNA ligase has to do in any case. But maybe this process makes the hopping, so the jumping from one strand to the other, less favorable, less probable. So possibly once the structure becomes smaller, our interpretation is that the enzyme basically doesn't need to hop from one strand to the other to reach a different ligation site. Basically folding the one-dimensional diffusion of the enzyme enables enzyme to find all of the staples and ligation sites and therefore ligate the full chain. So if you think about using the ability, harnessing the ability of ligating structures, creating more complex structures at the nanoscale, and therefore ligation is essential in this process. Imagine you can create a gram of synthetic chromosomes, okay? This is just an idea. If you can do something that is really the size of real-life chromosomes, like 100 megabases in length, you would need just 10 to the 13, quite less than before, but 10 to the 13 DNA unique structures for encoding 1 gram, 200 petabytes of information. And now if you think about manipulating this in nanoliter droplets, something that can be done with microfluidics ideally, but not under the scale, of course. Now, the total volume you need for containing 200 petabytes is no more one lake, but just one room of about 10 cubic meters. So even though we are still fighting to achieve somewhere close to this line, okay, this point in the line, in the timeline of IT development and technologies, this just harnessing nanostructures, harnessing reactions in nanostructure can actually boost dramatically the ability to implement this memory storage device scheme. All right, so the work was done essentially by Dorothy Aboagye-Mensah, who's in the audience, as part of a PhD project, and also other collaborators that are members of the Bragg Centre, or were members before, like Abimbola Adedeji, now in Sheffield, or Lakshmi Kailas, that is actually in Bragg, and thanks to Neil, Alex, and Alan for their collaboration, and thank you for the attention.
Thank you very much. Thank you very much, Matteo. Are there any questions for Matteo? I see one from Tom down here.
Well, while other people think of questions, that was fascinating. Thank you. The molecular dynamics simulation you showed, Matteo, indicated that the fluctuations in that ideal triangle structure, planar, are very, very large. I mean, actually, they look non-linear to me. But I wondered whether those fluctuations couple to the diffusion of the ligase, or wonder whether on ligation, there's any control or suppression or change of the structure of the dynamics of the system that then might couple to the induced or the landscape into which the diffusion takes place. Yeah, that's actually very possible. So in a sense, the second part you said is that when the ligation occurs, essentially change the ability of the enzyme to fluctuate. The ability of the structure to fluctuate and the enzyme to move. One aspect is given by these reactions, in a sense. If I go back to, probably if I had a keyboard would be better, but I don't think it can go much faster than that, I'm sorry. Here. So one aspect here we address this point is by using different number of sites in our ligation product. So even though you increase the number of sites that can be ligated, the total ligation product doesn't change significantly. Where are you pointing at? Sorry. Oh, sorry, here, the V5O. I can't see. Sorry, I didn't see the. So we have more ligation sites there, okay, in this structure here.
And with that one. So by studying by varying the amount of ligation sites and studying how this affects the ligation of the same chain, we could see that ligation occurs even elsewhere, but overall the structure of our pattern is more or less the same. So it is actually non-affected by the presence of other ligation sites. So local structural changes due to ligation that affect the fluctuations certainly occur, but are not the dominant component for the correlation effect. The different aspect is, the first part of your question is, well, we don't have a way to model the diffusion of the enzyme. We certainly know that the binding will depend on the fluctuation, but it is an ATP-driven reaction. And that means that the enzyme will do everything it can to stick to the DNA and swing around it and search for ligation site. This process has never been detected or studied at the computational level. It's actually very difficult to merge coarse-grain analysis of the enzyme with the coarse-grain analysis of DNA. We don't have a unique language. We use oxDNA for accounting for the DNA fluctuations using coarse-grain analysis in a detailed way, but we don't have a computational model that can visualize both processes together. I expect that these fluctuations have a role in the diffusion, but we don't have a way to see diffusion in a computational model.
Thanks.
I think there was one from Giles down here at the front.
Thanks. This is probably a bit of a similar question in retrospect to what Tom just asked. So I was just wondering about the kind of the torsional freedom you might have locally, which may affect the ligation taking place, which could well be changed by the different geometries that you have there. Do you have any comments on that?
Yeah. So we have done this. This was our first interpretation. By changing geometry, we changed the fluctuations, and we changed the ability of the structure to accommodate the enzyme in different positions. So in that sense, these structures here, the V1, V2, V3, and V4, are intended to address exactly that point. So we have simulations showing the fluctuations changes in V1, V2, and V1 and V2, and a form of V3, something very similar to V3. So we have actually simulations of V7. So we have seen that the fluctuation changes between V1, V2, and V3 are already, they massively change with respect to V0, that they should already be giving a complete different output. So V7, just the fact having just as one single trapezoid doesn't change significantly in our simulation with respect to V2 or V3. So the concept is, locally, we don't expect significant changes because the point is the structure of the triangle has basically assumed two metastates. So there are three elements of DNA conflicting against each other for fluctuating. So the system is a metastable system that either is bent like this or like that. So by fluctuating between two states is the main game in creating variations in the spacing between DNA molecules. Once we free the system from the mechanical resistance of each element, so now we have in the triangle, we have equally contributing segments. But once we break one of them by adding defects here, or in both of them, we already enhance the fluctuations of the bottom part. And this doesn't change significantly when it is completely alone. So by seeing this as an element that basically clears the air from thinking that local fluctuations are depending upon the presence or the lack of a single segment, we understand that we should expect some big changes in these systems already without going to this case. So the big difference between the performance of the simple defective structures with respect to the complex defective structure is really unexplained. Another aspect that cannot be very easily explained with the simulations is why do we need, why having one element flanking or near the ligation sites gives a higher yield than having the same element on the other side. So the diffusion interpretation is actually able to account for that because we have more edges here. So there are two components, two DNA edges, two reams of the DNA nanostructure rather than having only one. So by basically thinking that folding the diffusion, the 1D diffusion in 2D shape has to do with how many turns the scaffold makes, has a role on the diffusion, seems to explain our results. We don't have, however, a direct visualization of the process. That should involve some real-time AFM imaging. That, however, is a kind of very, very daunting task.
Okay, thank you. If there's any quick burning questions, then perhaps we can fit one in, but I suspect everyone's started eating their programs and are ready for lunch. So I don't see any hands going up. So I think we should thank Matteo for an interesting talk, and we can close that session. Thank you. Okay, so we have now reached the end of, well, the morning session, even though we're actually in the afternoon now, and it's now time to get some lunch. So anyone who is wearing a lovely Bragg lanyard, if you wouldn't mind gathering at the front, that includes management committee who may not have picked up their lanyards this morning, and all of our invited speakers and internal speakers. Everyone else, if you would like to head to the back of the and down the stairs, then food is being served in the refectory, and the event staff at the bottom of the stairs will help guide you across to the location. Sorry? Yes, so restart time in your programs, we are aiming to get going at 2:30, so please come back across in plenty of time.
I can't do without you. when you're the only thing I think about. It's all that I can still do, and you know you're the one I dream about. I couldn't do without you.
It's a very long molecule. Maybe you can look at it as a string.
DNA is 2 nanometers in diameter, but you have nearly 2 meters of DNA in every single cell in your body.
You have got 2 strings that sort of come together and they wind around each other. And on that string, you have got 4 different elements that you can array in a certain arrangement, and they are called A, T, C, and G, and we generally refer to them as DNA base pairs because they bind to each other in a specific way.
DNA origami is a technology which takes DNA molecules and forgets that they have any form of connection to life. It treats them purely as a building material.
So if you forget about everything to do with life in terms of the DNA and try to exploit the only thing of the DNA that it can bind, that it can have 2 different strands and they can bind together in a programmable way.
It allows us to start building shapes out of this by programming how these elements come together. We're now approaching the era in this field where all the applications are starting to emerge.
Applications are relatively wide-ranging. So if you can imagine, you can make flat things. You can make an origami that is an entirely flat structure, but then you can also make 3-dimensional constructs from this.
Some of the applications are in areas such as building molecular structures, but on the other scale, we're moving all the way into things such as diagnostics and medicine.
My research uses DNA origami to sense circulating tumor DNA.
My research is focused on the crystallization of different inorganic components.
In our application, we're using it for diagnostics. And I think what's really rewarding for me and very satisfactory is to really see that our technology has a direct impact in the clinical setup.
Imagine that you can create objects out of DNA that you can put drugs inside of, so little boxes essentially. And on the outside of the box you have targeting agents which bind only to a cancer cell. So when you inject that into your body, this little box travels around, and only when it reaches the cancer cell does the lid open and it release the drug at the target, rather than the chemotherapy that we have nowadays, which attacks everything.
And it's sort of still in the development stage, and then when it can actually be implemented in clinics and things like that, I think the impact will be quite big.
I find really exciting the fact that we can use DNA as a building object, so that we can practically use it to build up object on a nanometer scale, which is quite difficult to do in other ways.
The DNA Origami Iris project, it's a very exciting, very interesting project which will give you loads of different skills, not only in computer science, but also in understanding the biology, but in thinking of things in terms of chemical engineering and the physics of how objects interact and work at these length scales.
Practical lessons at school like woodwork and metalwork? Well, here's something you probably didn't have as a hands-on subject: DNA. 2 Yorkshire schools have been taking part in a project which has pupils shaping microscopic structure which could change the face of medicine. Our reporter Kathy Killick donned her lab coat and headed off to St John Fisher Catholic Academy in Dewsbury.
The work they're doing is postgraduate university-level material science. It's called DNA Origami. They're taking individual segments of DNA and merging them together to build microscopic shapes they've designed. It's cutting-edge science designed to inspire as much as educate.
It's been amazing. It's given me a chance to, get more analytical skills and get into research and topics which could be studied at PhD.
I do textiles, and my textiles project currently is on chemistry. So it's allowed me to expand in other subjects as well.
I'm genuinely finding the research behind all of this and research into vaccines and everything like that so interesting. So it's really has opened a door for me.
How can so much information be contained in such an exceedingly tiny space?
It's more than 50 years since Crick and Watson discovered the double helix structure of DNA. Now we can pull apart the helix and use its segments as building blocks to make something new.
So balance the tip on the inside of the tube.
Andy Lee is from the Bragg Centre for Materials Research at the University of Leeds. He's helping teach lab techniques and technologies unheard of just 10 years ago, essentially programming DNA to build itself into whatever they want. In this case, smiley faces. What else?
There's lots of really fascinating topics that are not touched on in textbooks, and it's my life's passion to actually pass that information on and get people as excited about those as I am.
They are creating, smiley faces that are 100 nanometers across. So you're talking a molecule that's made of nearly 500,000 atoms. But once again, the scale of it, you could fit, a few million of them in the side of a pencil. But they're doing all of that in our lab. That to me has blown their minds.
Scientists these days need to start young. This project hopes to capture capable minds and coax them into science careers where they can make new discoveries of their own. Kathy Killick, BBC Look North, Dewsbury.
I often wonder
probably do consider myself to be a very proud nerd. Yeah, I love research, I love science. That means I'm a nerd.
Oh, interesting. When I need to be, I'm definitely a nerd. But other than that, I would say I'm just like anyone else. You know, I like my binge watching telly and cooking and, normal stuff.
Well, I think my boyfriend would certainly tell me that he thinks I'm a nerd. But that I think says something about how excited I am about the science that I do, that when I get a problem in my head, it's something that I want to talk about all the time. And those problems or those scientific challenges aren't necessarily what's always interesting to everyone else. So in that sense, I think that is a type of being a nerd.
I'm not sure if I think of myself as a nerd. I wonder if maybe the fact that I feel like I need to have a definition for what a nerd is to be able to decide if I'm a nerd is maybe means that I am.
One particular barrier in science is sort of each time you learn a little bit more, you kind of specialize a little bit more. So even though you have the broad skill set, but what you want to do kind of narrows and narrows. So identifying what you would do next could be a barrier. But again, like with anything, if you're ready to learn something new and persevere, you will get to where you want to get to. Sometimes, yeah, it has been a personal barrier because I did my PhD analysing artwork. There was slight biases when I was trying to apply for jobs afterwards, even though I did do a science degree, basically. I did have a friend of mine who was a physicist basically tell me, "You're getting a PhD in chemistry for looking at artwork?" And I was like, what? Coming from a scientist, say, but you do have that in, I mean, people are biased, right? At all walks of life, scientists are biased too. So, but I guess there are people out there who do look at your skills as well. Scientists come in all shapes and sizes, and they don't all wear lab coats at the same time. You can have a scientist who works completely on the computer, or you can have scientists who literally work with pen and paper.
I think unfortunately there's a picture of a sort of senior white man that comes to mind.
The stereotype that I think is most common of a scientist is someone who is a genius and they're working alone. Maybe quite often it's an older guy, a man with a big fuzzy beard.
A typical view of a scientist is probably older, most likely male, and probably wears a lab coat and sits there playing with test tubes. That stereotype might have been right at one point. Nowadays, it's certainly not right.
And that's really not the case in any area of science, that these shouldn't be closed to people from any race, any gender, any background.
Anybody walking on the streets, they could be a scientist, and you never know. Because at the end of the day, it's what they do, what interests them, and it's not what they look like or what they wear or anything that would tell you that they're a scientist, for instance.
One of the people that's really influenced my choice of pursuing an academic research career in particular, I think, was I was working in a lab as an undergraduate. I was lucky in my university to have the opportunity to work for a number of years as an undergraduate researcher in a laboratory. And that meant working very closely with a number of PhD students who were working in the lab at the same time. And one of the PhD students, I think, at one point just said to me, "You want to be an academic someday, right?" And I don't think I'd really thought about that as a career path that I was going to pursue. But someone telling me, "You could do this, you want to do this, you could do this," made a big difference. And so that PhD student sort of framing that for me in a very concrete way, I think got me thinking, do I want to do that? How would I get there? Oh, I'll do a PhD, but beyond the PhD, where's that going as well? And having that exposure to the idea, I think that made a really big difference to me. So I think representation and visibility of role models is absolutely essential. As a gay scientist, I have been significantly impacted by seeing senior professors in my field who are out scientists, and that's given me confidence knowing I could have a career like these people. People have been successful who look and are like me, and that's had a big role to play for sure. And I think that's an area where science and engineering could do a lot more.
Every day I get to do something different, and I can make research as fun as I want to make it. So when you start getting interested in something, you can just keep running with that. So science is 100% fun.
At the core of it, it definitely is. But I guess like with everything, there is some extent of bureaucracy or paperwork that you need to do. But if you get past it, and if you can keep up your spirit when things don't work, then yeah, when you get the results that you were expecting, or sometimes even unexpected serendipitous results, then that's very joyous. That's definitely joyous.
I definitely think that science is fun. I really enjoy doing the practical side of it. I think it's really kind of fun to get in the lab and try different things out. There's having to think of new ideas and new ways of doing things, and I find that really exciting. It also can be really hard, so there's a lot of challenges, but I think that makes the positive sides when things do work. I think that makes it even more exciting.
I think there are parts of science that I find really exciting and really compelling. Those are probably words that I would choose more than fun. There are parts of science that are putting in the hours and doing really backbreaking work to analyze data and carry out an experiment. There is a reward to be had from that, for sure. I think it's a deeper sense of reward.
What I really like now as a scientist is being able to do a job where to think and I problem solve, and yeah, learning new things and making kind of discoveries and being involved in teams of people that are making discoveries, but also that I get to do something practical. So the job that I do now, I have to work in the lab a lot. I work with PhD students who I'm training, and that's something that, yeah, it's really important. Actually doing the science day to day and kind of fixing equipment, while also being able to be involved in kind of thinking about things, the two sides of it, practical and thinking, is something that I really enjoy. That's what drives me to carry on doing this job now. I think the piece of advice that I would go back and give to myself when I was 16, for example, would be to not worry about having a linear plan and trying to achieve kind of one goal. I think I would want to tell myself that the things that happen along the way, the opportunities that you have and the detours, and the kind of way that you live as you go through that kind of career progress is the important thing, not the end goal that you're trying to reach.
Good afternoon, everybody. Welcome back after lunch. Hope everyone had a fill of lots of tasty lunch. So we're all back seated. I'm pleased to invite you back to the second half of the Bragg Exchange. So we're going to move into session 4, which is functional surfaces. And following the same format, we're going to have a first speaker, some lightning talks, and then an internal speaker. We've got then another break. We're going to then have a second session, and then we're off across to the Bragg building itself to then have our drinks reception and posters. So again, a busy afternoon, so hopefully you did fill yourself up at lunch and take a rest. So it gives me great pleasure to introduce our first speaker for the session. I was hoping for the session slide, but Professor Jaz Pal-Badile from Durham. If you'd like to please invite you to the stage.
Great. Okay, great. Okay, good afternoon. So first of all, I'd like to thank the Bragg Centre for inviting me to give this talk. I hope to give you sort of an overview of the kind of research that we've been doing. It's got quite a high level, and then obviously I'm happy to answer questions which are more detailed. Okay, so in my talk, I'm really going to talk about some fundamental science, and then also how, by having a vision in terms of, where that science can ultimately impact and benefit some of maybe the taxpayers who've been paying, salaries and for grants and things like that. Right, so surfaces, which is, the theme of my talk, they're everywhere. We come into interact with, the 2D world all the time. And in terms of sort of, societal impact, that top sort of, atomic layer, few layers, can completely change the performance of a material or a device. And here are just some of the examples of the kinds of things that we've done over the years. And things like, sort of contact lenses, for example, just changing that outermost layer can make, change the biocompatibility properties of that material. Microelectronic devices, again, in terms of making them waterproof, food packaging, keeping food fresh, and even sort of, the drag reduction on the nose cones of Formula One racing cars. So in terms of the research itself that we do, basically, you've got surfaces, but it's the intersection. It's the sort of, the effect of the interface between surfaces and different disciplines. That's where we kind of find that it's good sort of opportunities to do good science, and then try and come up with various impact cases and things. So within my group, I mean, over the years we've had sort of, researchers, learnt about new areas of science in all of these areas, and that's always been sort of a theme, is to kind of always go and explore at these intersections. Okay, so the overview of my talk is that I'm going to talk about, first of all, sort of how over the years we've built a surface toolkit. So this is very much kind of, fundamental science, what new concepts, what can we do there? And then obviously I'm not going to have time to talk about all of these, so I'm just going to give you a couple of examples of how, after having developed that sort of fundamental science, how we've then tried to be able to sort of make surfaces which do particular things by having particular functionalities. And then towards the end of the talk, I'll talk a little bit about scalability, about how sort of taking it out of the lab, how to sort of, motivate your research students to go and do that for you, and have an impact on the world. Okay, so when we started out on this, basically we were interested in sort of, adding value, taking that top atomic or molecular layer and changing the chemistry of that. And so there was a range of sort of techniques that were available at the time. So there was things like, chemical derivatization, the kind of work which was done at Harvard and, the printing industries in the 1950s, where you have some kind of, functional chemical group which attaches onto a specific functional surface. I mean, self-assembled monolayers would be a good example of that. And then there are other techniques using enzymes and and electron beams and things, which were all, again, sort of either directional or they were very specific to substrates. And so when I came into this area, it was all self-taught. I knew nothing about plasmas. My background was in heterogeneous catalysis. But I was just curious to find out about these electrical discharges and what they could do. And the challenges that was to sort of devise sort of ways of functionalizing surfaces, so you could potentially take some kind of chemistry or methodology which you could apply to maybe a textile, you could apply it to a microelectronic chip, you could even apply it to humans, human skin, for example. And way back then, this is 30 years ago, as well as being low cost, environment was something that we started to take into account, sustainability, because a lot of chemical processes used a lot of toxic chemicals and chemical waste, etc. And then, as I mentioned, this substrate-independent thing, making sure that you can apply it to different things, because you don't want to go back and have to reinvent things every time. So these plasmas, basically fourth state of matter, and in nature, they're around, and there's even a theory about how sort of human DNA originates from lightning and all that kind of stuff. And so effectively, what they are, they're ionized gas. And what particularly intrigued me as a chemist was that the way that these plasmas are generated is that it's an electrical cascade process. So you can have very low amounts of energy, and you get an electron hitting an atom or a molecule, it generates 2 electrons, you get this cascade process. So energetically, it seems very favorable and sustainable as well. And in terms, again, of chemistry, if we think about sort of, if you do a chemical reaction, you need something which is going to get activated or excited. And if you try and do it thermally, you have to go to tens of thousands of degrees Kelvin before you can actually, start breaking atoms apart and all this kind of stuff. But by using these plasmas, by using these electrical discharges, you can actually generate these very reactive species at room temperature. So, again, this is very energetically efficient. And so potentially it opened up routes to carrying out chemical reactions. So, okay, but it was 100 years. Langley had been sort of playing around with plasmas for about 100 years. So the question was, why hadn't people already done this? And the problem was this. In the 1960s, they tried a lot. When there's a whole thing about sort of nuclear energy and things, is the control of the reactions, because you've got this cascade process, you get all kinds of reactions occurring, and therefore it's very difficult to get the kind of selectivities that you can get using conventional chemical processes like catalysis. So plasmas are basically, as I've mentioned, ionized gases, and they're all very lots of different types. There's fusion, for example, where people are looking at energy. But the particular types that we were interested in were called cold plasmas. So these are basically where the electrons are excited, they have relatively high energies, but all the other species, the heavy species, the atoms and the ions are all very cold. So they're at room temperature. So effectively the whole system is at room temperature. Right, and so in terms of sort of economic and environmental benefits, some of the sort of the traditional sort of just plasma processes which are used, you can see that at the bottom here we have all the kind of sort of chemical and energetical inputs into the existing processes, and how all of those can be repeated, removed by using a plasma chemical process. So in terms of environmental sustainability, the whole technology was very attractive, but just not in fashion at the time. Right, and so the big question, the big question in terms of science, which I've been trying to address, I guess, since becoming an academic, is that what I want to do is I want to basically, you have a chemical reaction, normally if it's uncatalyzed, you have an activation barrier. And if you have a catalyzed reaction, you can lower that activation barrier. And what my goal is to try to basically, rather than using catalyst, is to actually use an electrical discharge, use the electrons to be able to produce, with very high selectivity, chemical processes, because they'll be very environmentally sustainable. And so we started off, because obviously you have to get funding for this, and I started off doing this by basically trying to talk some American companies into funding this research. So, and they were interested particularly in surfaces, and that's how I got into surfaces. So if you think about here, we just got sort of basically the two electrodes, top and bottom electrode, and you introduce a precursor into this gas gaseous region, and you have an electric field. It causes excitation, and you can see there's going to be a whole load of different reactions occurring. And what we wanted to do was we wanted to control those reactions. We just wanted to get one reaction to occur on a surface, and so we could then basically replace conventional chemical processes by just purely putting in the reactant and electric field. So there's no other chemicals involved at all. So that was really the starting point. And so one kind of coating that we looked at was to basically make polymeric coatings, which are made, put on using solvents, etc. And so if this plasma, this discharge is on all the time, what happens is it's continuous, and you get all this breakup occurring. So, in the late 1980s, 1990s, that's kind of what state of the art was. And so it's just basically, it was just a whole mishmash. And what's happening is that because if you look in the electrical discharge itself, the electrons are much lighter than the ions. And so the electrons, they'll move a lot faster, and you get this charge separation occurring. And so obviously, once you get this charge separation occurring, then the heavier ions, which are slower, they're left behind, come down and start hitting the surface, and that's how you get all the damage. So thinking was, well, okay, can we try and stop that from happening? So then we had to look into the sort of plasma physics of all of this. There's a lot of fantastic plasma physics work done. It's always done on sort of argon or hydrogen or helium, something very simple. And so what happens is that once this electrical discharge is lit, is that you get the electrons and they get accelerated, and you end up with electrons, low energies, which aren't going to be really harmful, and you get ones at the higher energies, which are the ones that cause all the damage. So our thinking was if we could get rid of those high energy electrons, then potentially that would be a way of actually stopping all this damage from occurring. So the idea was a very simple idea, was just, okay, why don't we just turn this on and off? And if we basically turn it on for a very short period of time, then there won't be sufficient time for this charge separation to occur. And if there isn't sufficient time for this charge separation to occur, then we won't get all these secondary reactions occurring and all this damage occurring. So in principle, that could be a way of getting very high selectivity chemical reaction pathways. So by pulsing this discharge on and off, and by controlling that on time down to microseconds or even shorter than microseconds. Okay, so this experiment took 15 years to prove that this would actually work. So this is the example. Basically, we built a mass spectrometer which could do very high time resolve studies. And then we took a molecule. So the idea here was that the way conventionally Teflon was put down was using quite a lot of nasty chemicals, and the coatings are quite thick. But it's just the surface, it's the top atomic layer of Teflon, a molecular layer of Teflon, which gives you all the liquid repellency. And what this shows quite beautifully is that basically we're looking at the ions. We've got the precursor at the top, and it breaks into two stable intermediates. And one of them is a byproduct, and the other one is a CF2, which then goes onto the surface. And it puts down a beautiful Teflon-like layer. And you can prove that by using surface analysis XPS. And then, it's a mass spectrometry which really proves that what the chemistry is. You can see the ions are basically coming on when the plasma is on, that short pulse on time. But then when the plasma goes off, you can see that the radicals, the neutrals, are lasting for a much longer period of time, and we're getting very, very high selectivity. So that was kind of the proof of concept there. And then, so what you can move into now is you've moved into a whole new regime of chemistry. Is that you've got the conventional sort of continuous way where you're getting all these reactions occurring. People have been trying for 50, 60 years trying to control them. And then down here, you've now got the on time and the off time. And you can just tune those quite independently to carry out specific chemical reactions. So then you have a way of actually controlling what's happening at your surface in this particular case. So we've gone from the left, same precursor, getting something like that on the surface, to basically activating that double bond in that particular molecule there and being able to make a conventional polymer, but being able to stick it onto anything, because the thing is that the electrical discharge, when you turn it on, it generates reactive species, and it will generate free radical sites on any substrate that you've got. And furthermore, it's gaseous, So you can take something like my jacket, you can put it inside a plasma chamber, and every single fiber of wool will get coated with 1 nanometer, 2 nanometers, whatever you want of that functional coating. So it retains its porosity. And in terms of chemistry, just in terms of showing how sort of sophisticated this can be, is that we've got a molecule here on the left. I'm not a polymer chemist by training, and I remember when I first started looking at this molecule, I was told by some very eminent polymer chemist from overseas that you can't polymerize maleic anhydride. And in fact, you can if you use a pulsed plasma, because you can selectively activate the double bond on the left, and that will then polymerize, and you can retain those very reactive functional groups on the right. On the right there on the XPS, you can see that sort of where the arrow is, that's that functional group, and you can change the number of those groups on the surface by just changing the duty cycle. And we've used that, for example, in wound bandages to sort of incorporate things like dendrimers for drug release. So you can control it just quite simply by changing that duty cycle. And then just to prove that this really does happen on the molecular level as well, we've got time-of-flight sims here. On the left is continuous wave. So you get all kinds of species being made. And then on the right, you can prove that by pulsing it, you've basically got the fragments which correspond to that conventional polymer. So no solvents, no catalysts, fractions of a milliwatt of energy to do this. So the concept was born in the sense that, company would come along, they would say to us, we want functional group X on the surface. We would say, okay, it's going to cost you this much. We would then go away, look up in the Aldrich catalogue, the functional group to use, and then we would basically put it down. And so that was basically the way that we kind of started to sort of expand on that sort of fundamental science that we'd done. And then some of the benefits, I've mentioned them already, but I guess, by controlling these lifetimes, you can control the density, but also you can make gradient layers. So you can actually, by just changing the duty cycle, you can change the gradient layers. You can also, because you can put down nanolayers, you can make multi-layers, you can make functional nanolayers, and I'll give you some examples of that. Okay, so I'm now just going to move on to the next part of my talk, having talked about sort of the fundamental science. I'm now going to go on to talk now about some examples, just to show you how we've taken that from the lab. Students have done the work, they're very motivated, and try and get them to get out the lab, mentor them to do startup companies, and then hopefully help them develop their careers. Right, so the one that we started off with was Teflon, because DuPont were funding a lot of the work. And so basically, in terms of liquid repellency, people talk about Teflon. It's got a surface energy of about 18 dynes, which isn't that great, actually. It's not very low. It repels water, etc. The basic chemistry is that fluorine is the most electronegative element in the periodic table. And so if you can basically put down perfluoroalkyl groups, and the minimum length is six CF2 groups, then that terminal CF3 group has basically all the electrons being pulled away from it. And hence, that can significantly lower the surface energy and increase the liquid repellency of that surface. So that was the concept. And there's a history to that, but it basically ended up saving quite a lot of lives in the Iraq-Iran war as well, with the military. But that was the basic concept, how can you repel liquids? So the state of the art was that basically, you can buy these sprays, and when you spray them on a surface, the conventional way, they've got all these other chemicals in there, and that's going to make that surface impure. So if you've got any kind of other chemicals in there, it's going to basically raise the surface energy, so it won't be as good at repelling liquids. By using our method, you're just using the pure ingredient, and therefore, you will just get a much better quality surface. So X is going to be a perfluoroalkyl group that I've just mentioned to you. So here we've got basically the deposited pulsed plasma system in the middle. On the left, we've got continuous wave. And on the right, we've got our colleague synthetic chemists to make the conventional polymer. And you can see that the two time-of-flight sim spectra perfectly match up. So this proves, again, that we can actually make these conventional structures, which would take catalysts and all kinds of things. We can make them in a very efficient way. And just to get the surface, we can put down very, very thin layers. And then, okay, so in terms of surface energy, you can see there's Teflon. That was kind of what state of the art was using those sprays, and ours was right down at 2 dynes. So very, very liquid repellent surfaces. Okay, and then to show you that, these coatings, you can retain especially breathability in textiles. So here we're putting down 2 to 5 nanometers on each individual fibril of cotton in this case. So you can still see all the cotton fibers on the fabric. You can see that it repels water and it repels oil, and that's engine oil. Okay, so here's a quick example of the mobile phone. So because it's a gaseous process, you can basically treat the whole phone, just put it straight into the chamber, and you can see that this completely retains its functionality. So that's a very sort of easy market to get into because, as I'll tell you in a minute, sort of million smartphones every day are dropped in liquids, in the bath or wherever, and get damaged. And so, the impact of that sort of annually, looking at sort of, over $100 billion in terms of smartphones being damaged. And so, we went ahead, sort of, a PhD student basically scaled this up. Production line there in Texas in the middle there on the right. 90% of hearing aids in the world now use this technology. Okay, so hearing aids. Obviously outdoor wears. This is quite old now, 62 factories across 5 continents, and over 1 billion electronic devices have been protected using that technique. So it's an example of taking a very fundamental scientific idea all the way to the market. Okay, I'm now just going to move on onto some, I guess, a different approach now. So this is basically looking at slippery surfaces. So this is a different way of repelling liquids. And the fundamental concept here is that we've all heard of sort of benzene rings, aromatic rings. And basically you have two sort of, imagine having two sort of aromatic rings next to each other. Because of that electron cloud, you can get sort of pi-pi interactions. So you can get some kind of interaction there. And so there's an interest in making surfaces which are slippery, and the people have talked about there are plants, for example, where insects can fall in, and you make rough surfaces. But the thing is that by making surfaces rough, you have to put quite a lot of liquid in. So we thought, well, actually, there may be another way to make these slippery surfaces, which is have a very smooth surface. And if you can put these aromatic groups onto the surface, and liquids can interact with that. And that's exactly what we did. So we basically put down a functional group where the functional group is now a phenyl ring. And then onto that, you can basically attach a liquid, and then the surface becomes slippery. The liquids will just roll off. And so I'll just show you an example of that. Okay, so we've made a surface here now which has got a surface which has got basically aromatic rings on it, and then we've just basically impregnated cinnamaldehyde which has got aromatic rings on it. And then, that should be working. There we go. Okay, so we've got tomato ketchup here. So you can basically see that on the left, the tomato ketchup isn't coming out. And there we go. On the right, we've got the one which has basically got these aromatic rings, and then we've put cinnamaldehyde on there, and you can see it just comes straight out. So that gets all your tomato ketchup out of the bottle. And you can do that with other foodstuffs as well. So it's a good way to sort of improve, get rid of food waste. Okay, and then we had COVID and lockdown, and so, for 30 years I'd been sort of, working in my lab doing experiments every day, and then suddenly I'm sort of, restricted to being at home. What am I going to do? And so we have a lot of international projects, and people, looking at sort of, especially in developing countries, how can you sort of contain the spread of COVID? And so basically, I came up with this sort of idea about basically, we have tea stains. And tea stains are actually a way of making coatings. And so, you can get tea in most parts of the world. And then, so the idea was if we basically use these tea stains, and basically in the tea stain, there are these aromatic groups. You have aromatic compounds in tea stains. And so you can then actually introduce other compounds into that to get sort of these pi-pi interactions, which I've talked to you about. And again, I'm just using cinnamaldehyde here. And cinnamaldehyde, cinnamon sticks, again, you can get these from all around the world. You can get cinnamon oil. So if you impregnate cinnamon oil into sort of, brew some tea, put some cinnamon oil in there, and, dump your substrate into it, mask or a glove, take it out and dry, you will get a very good antimicrobial coating because the cinnamaldehyde is antimicrobial. And so what we did was we took that one step further. The university wouldn't let me go into the department because of COVID. But on Amazon, you can actually buy copper sulfate, silver nitrate and things. And what you do is if you put silver nitrate or silver nitrate or copper sulfate into your tea and cinnamon oil, you get these coatings which have now got the cinnamon oil impregnated into it due to the pi-pi interactions, but also you get reduction of the silver or the copper into nanoparticles. So you end up with a composite coating, so it has dual functionality now. It basically has got the antimicrobial activity from the cinnamon oil, which is a natural product, but it's also got the antimicrobial and actually antiviral activity of the silver and the copper. So then we basically got tests done in Cambridge, and we were able to show that these coatings can be easily made anywhere in the world, and they're active against coronavirus and the spread of coronavirus. So it's a very simple example of pi-pi interactions and how you can use them, and again scale them up. Okay, so just moving on, so you can probably tell when this work was done. You can use the plasmas to make these nanolayers, and I'm going to quickly show you an example how you can use that as a scratch card technology for biomedical applications. So because these layers are so thin, we can control them. We can put down an active functional layer of, functional group X attaches DNA, protein, or whatever, and then we can put a protein-resistant or a cell-resistant layer on top. And then by using just a standard conventional spotter, and we can actually spot proteins or cells or whatever you want to, because the layer is so thin, it's like pricking a balloon. So when the spotter tip comes onto the surface, it will just puncture that area. And so here's just an example. You've got AFM on the left and in the middle, and then on the right, we've attached sort of a protein and then the complementary protein to show that this concept works. And then you can make protein arrays for proteomics, again, using the same kind of thing, spotting different proteins, and then you can use that for detecting things. And you can also make cell arrays as well. So, if you're looking interested in how cells interact, you can have a cell-resistant background. You can see where it's been punctured. You can grow cells. Right, okay, so now to sort of move on from sort of technological to sort of societal impacts. So we have an interest in, having done all these sort of startup companies and things, I realized that basically, it didn't matter, I mean, it's much more interested in science than trying to please venture capital people and all the rest of it. So I wanted to do something different. So I'd never really traveled abroad, and so I got sort of interested into sort of looking at some of these other problems. So it really sort of ticked off. I went to some developing countries, and in this particular town, they'd been taking DNA samples, and 65% of them had sort of DNA mutation. I went to another place, and there were kids who had uranium in their hair from drinking water, from contaminated water. So these are things which I thought would be worth sort of getting challenging and trying to do something about them. So, simple example here, first of all, is that we wanted to basically make surfaces which could remove water pollutants from water. So what we've done here is we've used this plasma chemical technique, because we can coat anything, it can be cloths and things. And we put down a layer, and then we basically impregnate it with cresoviolet, and then we can take that out, and we can make these very, very high surface area structures. You can see the pores. So this gives you a very, very high surface area structure, and that's what you need if you're going to try and make something which is going to remove something using a surface technology like capture and release. And so here we've just got some electron micrographs. That's just sort of the cloth, and there's the fibers. And then on each of those fibers in the cloth, you can see we've actually grown these polyhype, these very high surface area structures. And then onto those, we've got the functional groups onto which we can tether moieties which will remove the pollutants. So the first one that we looked at really was to remove agricultural pollutants, and we used cyclodextrins, which is very good at removing agricultural organic pollutants. So we basically put the coating down, we attach our barrel. So cyclodextrin is basically a barrel into which the pollutant will fit in. And then we basically put it onto these high surface area materials that we've made. And sure enough, they work. So these are the two controls at the bottom, just the cloth. just a cloth with a functional coating, and then the cloth with a functional coating and the cyclodextrin, and you get very good removal of this organic agricultural pollutant. And then you can regenerate. You can use the cloth many times by just changing the pH. So you put it into a bucket, you change the pH, and you can use the cloth multiple times. So this is another example. This is one of my PhD students. We went out to a developing country where they were taking goat skins, and they were then basically chemically treating them and then selling them to very high fashion handbag manufacturers. And as you can see, she's standing there, you can see that the water's coming out there. So this is straight from this particular sort of site where they were making these bits of leather. And that's full of chromium. And if you just go around the corner from there, you've got cows drinking the water that's coming out of this plant, milk and all the rest of it. And so what we've done there is in the collaboration with a group from Turkey, and we've been making these cyclodextrins here. Calixarenes. So these are calixarenes. So again, these are just very sophisticated, organic molecules. These guys had for years been making them. And what the clever bit we've done is we've been able to attach them onto anything, onto textiles. We attach them on, and you can see that basically we can remove all the chromium from the water, and we can reuse this many, many times. So we can take local cloths, local cloth, cotton, wool, wherever it is. We use our plasma chemical technique to put down our linker layer. We attach the calixarenes, and then they can remove the chromium. And so then you can remove that from the water supply. Okay, next example is oil water spillages, when sort of oil gets in, and this can have huge environmental impact. So how can we do this on a continuous basis? BP were ringing up, but it's too late. If something like that has happened, you have to have these technologies ready. So earlier I told you about sort of liquid repellent surfaces where you have these perfluoroalkyl groups, and they will repel water. And if the surface energy is sufficiently low enough, it will repel oil as well. But if not, they won't repel oil. So we basically came up with the way we wanted to make a surface which would switch. So it would be wettable. So it would be contradictory to what we have at the top there. It would be wettable, but it would repel oil. And we wanted this to happen on a very, very fast time scale so that we can actually separate the water from oil as it goes through a mesh. So first of all, just to show that the surfaces they're actually anti-fogging as well, which has been protected as well. But basically, this is an uncoated surface and a coated surface. And because the surface is hydrophilic, it will basically not fog up. So for spectacle lenses, but also because it's oleophobic, it repels oil, you won't get grease on your spectacle lenses. So that's a good example of an oleophobic hydrophilic surface. And then here we've just got a sort of a range of, the bottom one's the treated slide. So we've got sort of, olive oil and engine oil and things like that, and the surface repels those quite well. So we're going to take a mesh, we're going to put our functional coating on this switching coating. We're going to dye water blue, oil red, and then we're going to put it through the mesh. So there we go. So we've got the oil on the mesh. You can see the oil is sitting on the mesh. It's not going through. And you can see the blue water is quite happily sort of being separated out. It goes through the oil, and it's being separated out. So that's a static system. So here's a dynamic system. So here we've just dyed the oil red. The water is clear. And you can see that basically the oil and the water are being separated out. So there's a little bit of oil that's come through the mesh here, but you would just pour that round again, and you can separate the two things out. Okay, so we've also, in fact, Tom was at Durham when I got this EPRC grant, and this was basically, we sort of, again, sort of, pushing our knowledge, we sort of linked up with botanic gardens around the world. So in places like Peru, Mexico, Namibia, all these places, dry places where there isn't much rain, but plants survive. So we're interested in how do these plants survive, because it's a way of collecting water. Because one of the biggest problems is in the future probably isn't going to be oil, it's probably going to be water, because already it's causing mass migration of people where there is no water to drink. So we started to look at basically plants which grow in the desert, which collect water from the air. And the idea is to sort of set up nets or other structures, architectural structures, where water can be collected so people can actually live. They can retain their culture, which is very important, language, cuisine, all these things, and not have to sort of mass migrate and all the rest of it. Okay, so this particular example, I discovered with a colleague who were in the cloud forest in northern British Columbia. So it's always raining there, but if you look at this particular branch, you can see the water isn't actually going through the branch, okay? Although there's porosity in the branches there. And this particular tree species, what happens is, the deer and the bears and all this, they all go and hang out under these particular trees. So we're really curious, sunlight can get through, so you can get all sorts of photosynthesis and things occurring, but the water doesn't get through. So, is there something that we can learn here? Can we make, for example, tiles which could be used, in developing countries, so, you can get heat being released out to the building, but rain won't come in? Because, then that gets rid of a lot of, sort of air conditioning and things like that. Okay, so basically what we've done is we've taken the structure. So my student first of all just drew out what the structure was on the leaves, and then we 3D printed it. And so they've done a lot of studies in terms of structure, but in particular you can see you can almost get it horizontal and no water gets through it. So the whole nature has sort of devised this over hundreds of millions of years. These particular angles, it's the angles which are critical. So we've made the 3D printed structure, and you'll see that basically none of the water is going through the mesh. And when the camera turns around, you'll see that, in fact, there's holes there. So that's just going to come up now. There we go. So you can see these can be quite easily made, and there's basically no water going through it. So you then have to think about the situation where you have maybe, sort of rain, like lots of water coming. So what we did is we basically staggered them a little bit. So we're using solar cells. So light can still get through, but the small amount of water which gets through the top mesh will just basically get, it'll fall off of the bottom mesh. So we've got the shower head now, and you can see basically all the water comes off. Okay, just found this double layer structure. So this can be used in buildings. It can get rid of air conditioning. That's the main thing. Is that's what is using up a lot of energy. Okay, so then technology transfer, we can go from very small sort of robotic systems, which are used on car production lines, all the way to sort of, 1.5 meter width roll-to-rolls using plasma discharges. Yeah, so 3 sort of successful startup companies through my students. Yeah, summary. So most of the work has been protected by intellectual property, etc., which sort of benefits the university. Companies which have funded the work over the years, mainly the funding has come from industry. Fantastic PhD students. Most of the work has been done by them. And then some fun that we have. So wherever we go, we always try and sort of work with local communities and, just sort of give them the buzz about science, which Joe was talking about earlier. Thank you very much.
Thank you. Some incredible work in there. I suspect a future Nobel Prize for the ketchup in a bottle. Any very, very quick questions for Jaspal? I think we can field one from Joe. I think it's coming down now, but.
Hopefully this will be a really quick one. Firstly, I'm really interested to know whose phone got dropped in the goldfish bowl. And secondly, can I get my phone treated like that so that I can't break it again?
Well, yes, you can be treated. I mean, so the history to this is that I was away in Belgium, and I came back at a weekend. And we live in the middle of nowhere. And basically, loads of newspapers had been to our house, and we didn't know about it. So on the Sunday, what happened was on the front page of the main section of the Sunday Times was this story had been released while I was away. And so that was fine. Okay, university was very happy with that. But then people just started ringing us up with all kinds of things that they wanted treating. So to give you some example, somebody actually was serious. They wanted their cat treated. Another gentleman turned up with a hot air balloon in his jag. So yeah, in theory, anything can be treated. Yeah. Whose phone? Oh, we got hundreds of them. So it's
amazing. Okay, well, I think we need to move on a little bit, but let's thank Jaspal again, and then any questions can be in the discussion in the break. Okay, it's time for lightning presentations. So we'll jump straight to our lightning presentations for this round. For our poster speakers, if you could line up. Okay. So first up we have Robert.
Hello everyone, I'm Rob, second year Bragg PhD student, mostly interested in like soft tribology. I mostly look at polyelectrolyte functionalized surfaces on PEEK. They're used in like cartilage repair. There is a need for softer materials in orthopedic implant. Current use of hard materials such as cobalt chromal PEEK typically leads to quite large stress concentrations, overloading the cartilage erosion and early failure of the implant. So one solution is functionalizing hard surfaces with a soft interface, and one that's very good is any polyelectrolyte that is hydrophilic ultimately, and depending on how you graft them, the grafting density, you can kind of tune them to be elastic and resist the kind of loads you get in joints. So it offers like a highly hydrated and lubricious interface that you can put on current biomaterials. So to assess these, we'd slide them against some bovine cartilage at gate-like speeds and loads, so it can kind of vary the loading profile to what it's actually like if you walked on it. And while they reduce friction coefficients to what you get for cartilage interfaces, really, down to sort of 1 or 2% friction coefficients of 0.02 after 2.5 hours, which compared to untreated biomaterials is upwards of a 95% reduction. But more interestingly, they're also able to kind of exploit normal modes of biotribology. And one quite interesting phenomenon we've observed is that after a period of static loading and then sliding, they're actually able to induce dynamic cartilage rehydration and enable boosted lubrication in cartilage, which is kind of the modes of biotribology that maintain our joint health. So come to posters 16 to learn more.
Thank you. Next up is Gizu.
Yeah. Hello everyone. My name is Gui Zhi. In nature, the shell possess mechanical robustness, like high toughness, through their exquisite and diverse layered structure. So inspired by this, we designed a coating with similar exquisite layered structure with our coating machine in our lab. And the structure is confirmed by TEM. So it shows that the energy dissipation density is 2 times than the single layer coating. To scale it up, the 150 kilogram force indent shows lower crack density and more lateral cracks. The toughness enhancing mechanism should be the layered coating structure, acts as effective barriers to restrain the propagation of cracks, and such design might find its use in industry like gears and bearings. And thanks, and glad to see you at the poster session. Thank you.
Thank you very much. Next up we have Christine.
Hi, I'm looking at molybdenum disulfide-based coatings, which are most commonly used solid lubricants for space applications. So pure MOS2 is very susceptible to oxidation, therefore it's commonly doped with titanium to improve the resistance to oxidation, but it's not the most preferred coating. So how we analyze it? Well, we expose both coatings to various temperatures and monitor any structural changes with heat, and then link these changes to its friction and wear performance. And why is these results important? Well, it was actually found that in pure MOS2, the exposure to heat promotes water desorption and oxidation, but these oxides actually improve the overall hardness of the coating, which then improves the wear resistance, which is actually quite beneficial for space applications. Thank you.
Thank you very much. And last but not least, Amna.
Hi, I'm Amna. My project is the assessment of biodegradability of engineered polymeric microparticles using a simulated model. So microplastics are increasingly present in the environment. They come from primary sources such as garments, fibers in garments, and also in engineered they are also engineered into formulated products. And then after use, they get washed into wastewater and then into rivers and canals and then eventually the ocean, posing a serious threat to the environment and human health. So a lot of research has been done to develop biodegradable polymers and have shown various degrees of degradation. But it still remains to be seen whether they retain that degradation once they are converted into microplastics. So please come to a poster session and I'll discuss more in depth of the experiments that I'm doing and characterization. Thank you.
Thank you very much. And thank you to all our poster speakers for being super sharp and snappy this time. I think without further ado, we'll jump straight into our next speaker, which is Dr. Armin Sajapur.
No, he switches on up there, it's already. So you click it here, and there's a laser pointer if you need. Okay, great, thank you.
Okay, hello everyone. I'd like to first thank the Bragg Centre for giving the opportunity to talk about the recent advances in the structure formation in the electrospun membrane. So that would be mainly focus on the application of the X-ray scattering analytics into the system and how we can fine-tune the structures in nanoscale. And I'll talk also about some visions of the biofunctional application. So indeed, I'll go through fabrication, multistructural analysis, and promoting the hierarchical by kind of embedding the lipid nanostructures in the systems and the biofunctional opportunities. I would like to first kind of classify the whole talk into two different parts. One will focus on the polymer electrospun fiber itself, and then how we can introduce more complexity in terms of the embedding the lipid nanoparticles into the membrane. With the electrospinning, we are talking about the pump and the voltage applied between the needle and the collector, in which the polymer solution is being put inside a syringe and it flies over to the collector. And over the time, the solvent evaporates and we get the thin deposited layer. It is actually pretty much what we heard also this morning, and that was quite interesting, and I'm trying to put a different angle in terms of the X-ray scattering studies on that. So here we can use the flat collector, in which we would get the random nanofibers deposited, or we can use the rotating collector, in which actually will apply more stretching force into the polymers in solution, and we'll get the aligned nanofibers. And if you could just look into the membrane, if you peel it off from the collector, it would look like this picture here. And looking into the more micro and nanoscale, we've done this SCM image at the bottom. You see these nanofibers are being formed in different orientations. And obviously, this is the image of the X-ray scattering in the nanoscale, in the reciprocal scale. For those who are not familiar with the scattering technique, we are talking about a kind of nanoscopic imaging in which happens in inverse space. So whatever, let's say, long and thin appears short and fat in reciprocal space. So kind of, that's why it's called also the inverse space. What is interesting here, we are talking about the direction as well. If we have the random direction, random orientation of the nanofibers, we get a kind of circular signal in the scattering. And if we get it kind of oriented, we get the elongated signal. And that's also another aspect of the reciprocal thing. So if they are aligned in real space like this, the scattering image will align perpendicular to that. control of the processing conditions, we can have a look into different polymers concentration. For instance, here we have picked up the polyethylene oxide at different polymer concentration. You can see, at the end, you can optimize the concentration to get the optimum fiber diameter and uniformity at the end, right? So from 5% to 10%, you see kind of a non-uniformity along the fiber can be formed. And the fiber diameter also is increasing. So the diagram at the right-hand side shows the fiber diameter. But we can also have a kind of roughness on the polymer nanofibers. Okay. At the moment, we are talking about a few micron size. So if you could just look into the size distribution there. And here is how alignment can be done by using either the flat collector or rotating drum at the two different speeds. So if you go to the highest speed, you align the nanofibers more and more. And these misorientation coefficient is being calculated by the, again, scattering techniques, which I will show some introduction about how we can calculate that. But if we start from the beginning, that is PVDF, HFP, a non-aligned membrane signal. And what you do indeed, after getting this two-dimensional picture, you would just do the azimuthal integration and get this kind of signal. So for this type of semi-crystalline polymer, we get the peak at the middle of the curve and the overall decay. And the overall decay is a characteristic scale for understanding the dimensionality. So this one is mainly talking about the three-dimensional structure and confirms that we do have some crystalline crystalline feature in the structure. We have developed a model to kind of simulate the scattering peak, which actually refers to the decay function and the correlation function. And both of these two parameters have been correlated at the end. So the Poirot law talks about the uniformity, how the uniform or the interface of the fibers are rough. Let's say if we get the 10 to the power of 4 decay, it's quite uniform. And if we get deviation from that towards the 10 to the power of 3, then we do have more rough interface. While the correlation actually shows how the crystalline domains are being separated from each other. I'll have pictures about that. And this is the 2D Sachs profile of the, let's say, aligned nanofibers, right? So as you can see, we do have also the lobes appearing on either side of the thing. And that's actually the same peak which we were talking about and actually we call the correlation peak. By kind of decomposition of this curve into the two dimensions, we learn more about the dimensionality features in the membranes. So first one is the vertical direction. So actually kind of integrating this part of the curve, the red highlighted part of the curve. And as you can see, it's just starting from the non-aligned fibers, which shows this peak. The peak disappears gradually. While if we talk about the other side, the peak starts to highlight. This has a very important message for us, and that kindly says that we do have the nanostructures also aligned along the fiber. So it's not really randomly distributed. It aligns while we do the electrospinning. With the decay rate, I talked about the Poirot exponent, right? So remember 10 to the minus 4, smooth interface, 10 to the minus 3, or any deviation from the 4 is the rough interface. And here is what we see. The Poirot exponent increases towards 4 for the vertical profile, while decreases towards 3 for the horizontal. And that is another identification of the roughness alignment along the fiber. And overall, we could draw this kind of picture where if we say we do have the nanofibrillary structure, we do have the lamella or semicrystalline domains aligned in the direction of the fiber, and this kind of feature can be obtained from the peak position. We did also kind of wide angle or XRD studies for this semicrystalline polymer. As you can see, same kind of, let's say, orientationality is being achieved, and from that we could develop this kind of molecular model and do the analysis, and at the end we could also extend the feature of the molecular orientation in sub-nanometer scale along the fibers. And this slide pretty much shows the technique of the X-ray scattering where we can calculate the misorientation. It's called the, let's say, Rulin method. In principle, it is about analyzing the peak shape, okay? So again, you can see here the reciprocal scale orientation. If it is this way, the real space would be the other side. And what we do the azimuthal integration in the area, as you can see in this middle picture, and then we get the kind of peaks over there. And from the peak broadness, we develop this kind of relationship between the B observed, which is the angular spread, the peak broadness, as a function of the S, which is the actually scattering vector. And from that, we get a linear behavior, and these linear behavior could show the LF, which is the fibrillar length, and the B observed is the misorientation degree. So the intercept shows us how much this has been, the fibers are being, let's say, misorientate. Oops, wrong button. Yeah, that's the overview of what we could develop by different techniques from microscale to angstrom scale. Now, the idea was to make these electrospun structures, membrane structures, but more structured in nanoscale, and see if we can develop novel function for these kind of surfaces. So the idea was to pick up the electrospun membrane and actually embed the mesosomes. Mesosomes are kind of structures with meso hierarchy, or let's say nano hierarchy. And actually the aim was to make these particles embedded within the fibers. I will explain exactly what mesosomes are. It is already quite a big area in the field of the lipid self-assembly, but in a few moments I'll talk about that. It's talking about these kind of three-dimensional lipid hierarchy embedded inside the membranes. So how do we synthesize? First, we take the mesosome particles, which are the colloidal particles. Actually, inside we do have the, so this kind of particle, which size is around a few hundred nanometer. Inside we do have the lipid hierarchy, so self-assembled lipid particles, which actually they do have the hydrophilic and hydrophobic channels. So this specific one is called cubosomes, in which we do have the interconnected two continuous phases. Both phases, so these channels are connected to each other with the water channels, but separated by the hydrophobic lipid channels. Whole of this structure, so the cell, let's say, the lattice constant here is around 6-7 nanometer. So all of this structure is embedded inside the particle, and in the interface we do have block copolymer. Block copolymer is, in this case, we've used the Plurinic F127, which does have the PO, PPO, and PO. So hydrophilic, hydrophobic, and hydrophilic. And this kind of structure makes them to be stable. but at the same time compatible with our polymer, which later on we're going to use for the electrospinning, because the electrospinning polymer, remember, was a polyethylene oxide for us. So in that case, we did take the different polymer, polyethylene oxide lipid ratio, and looked into scattering profile, where the intensity as a function of Q, which is the scattering vector. Again, if you notice the dimension here is nanometer inverse. Again, inverse scale microscopy. Yeah? So starting with this red curve, which only shows the lipid nanostructures, we do have this fingerprint, 3 peaks there. And by addition, by increasing the polymer concentration or polymer to lipid ratio, these peaks intensity reduces. So this one is the pure polymer, this one is the pure lipid. But what is the message of this figure is, by mixing, we still keep the lipid nanostructure retained. So that's the kind of challenging issue, because most of the time we do have these structures disturbed or kind of unstable and so on and so forth. But a specific compatibility between the polymer and the lipid structure that we use, we could retain those. Of course, we could see a little bit of lattice parameter change over the concentration, which was not really much for our purposes. Here, we could also see how the ratio of the polymer to lipid could explain the diameter in terms of the relative humidity. Overall, by increasing the humidity in the environment that we do the electrospinning, the diameter of the fiber reduces. But by adding more lipids, let's say from no lipid to more lipids, we get the fiber diameter increasing. And this was the first instant that we could identify the lipids induce some structural changes into the polymer itself. And after that was in solution, and after electrospinning, the interesting observation was that these 3 peaks, which was the fingerprint for the cubic phase, you remember this nice 3D-dimensional structure, disappears, and we only see 1 peak, which is the indication of the lamellar phase formation. And we did also more analysis on really finding out that we do have the lipid particles within the fibers, the tomography studies, and the, let's say, microscopic studies as well. And here also shows after electrospinning how the lipid ratio changes the intensity of the lamellar phase appearing in the electrospun fibers. So far, so good. But the most interesting observation was after doing electrospinning, we do have arrangement of the lipids from cubic phase to lamellar phase. Internal arrangement is being done, but interesting was to see whether we can, after, let's say, water absorption or humidity absorption by these membranes, do we get the nanostructures come back as well or not? So what we did, we designed this kind of in situ measurements, where we put the nanofiber inside our fluidic cell. We put the vapor pressure inside the bottle and pass it through the membrane. At the same time, we shine the X-ray and recorded the images every minute. That was how the setup looked like in our laboratory. So this was the sample holder, X-ray coming from this direction. This is our pump setup, and that's how the fiber looks like inside the chamber. And we observe this kind of curves. So what is interesting here is we do have at the beginning the lamellar crystalline form with these specific peak orientation, and then the fluid alpha phase, still lamellar, and at some point they again arrange themselves back into the cubic phases, which was quite a unique observation. We did also some mechanical studies in which the tensile test, tensile stage is being put inside the X-ray instrument. We did the stretching and recorded the curves, which actually the data has not been fully presentable at the moment. But what we learned is these lamellar phases inside the membranes are also aligned together with the alignment during stretching, because while we stretch also we get the alignment. Okay, I think I'm running out of time. Just quickly about the biofunctions, what we envision to do. So this was a kind of a retarded release of the fluorescein dye model drug from the membranes, and cubosomes itself do have a lot of applications in the drug delivery with the, let's say, specific release behavior. So here we can see the green curve, which is kind of delayed release. But embedding inside the polymer, we get additional delay in the release. And we aim to apply this for, let's say, making the function, because of the biocompatibility of the lipids, we aim to apply also for more control of the cellular behavior, like antimicrobial activities or cell differentiations, or producing the cultured meat, or control of the texture in the product. So with this, I would like to finish the presentation and thank all my colleagues who have helped over the years, and thank you for your attention, and we'll be happy to take any questions.
Thank you very much, Amin. Are there any questions for Amin? I see one from Tom down here, if we can start there, maybe.
Yeah, hi, thanks. Lovely talk. The electrospinning, as you say, another. Don't think insects have invented that yet, but you never know. I'm interested in your low Q scattering. Slightly confused because I'm used to porod scattering being off surfaces, either rough or smooth, Q to -4, being therefore a high Q phenomenon for the very reason that you said. You're focusing right down on the surfaces of the fibers. So at low Q, of course, we're looking at long-range correlations, which are across many fibers. So I don't understand why you called it porod scattering, but I'm also interested that we see increasing scattering at low Q anyway, because that means we've got increasing correlated structures. It looks more like a critical point, and you have are there large clumps? So what picks up in the microscopy that could explain that large Q scattering? Because it's not really porod. Is it?
Yeah. Well, it's related to the system. So depending on which length scale we are talking, the Q, that the observation Q could be already long scale or small scale. Depends really on the scale of the material we are exposing the X-ray to. So in this case, we are talking about, of course, very big scale material. We do have features coming from already a few hundred nanometers as well. So if we had a machine which could give you a very, very broad Q, we would have more insights about and better judgment. Let's say if you're talking about nanoparticles of a few nanometer, then that view of the low Q and high Q would be quite established. But in this case, we are talking a very complex mixture of the long and big scale material and also nanoscale semi-crystalline domains.
Thank you. Does that answer the question? Are there any more questions for Amin? No, in which case then I think we move into our break, and I think there is coffee that's waiting in the wings to come through, which I think everyone's eager for. And then we'll move into our final session after about 10 to 15 minutes. Thank you.
bodies collide and keep us from getting cold. Skin pores open up and swallow each other whole. And the scars we collect connect and reverse the flow. And so it goes. Emotions motion us towards, and our last experiences serve us all. Each life that we take bores holes into the walls, till the roof caves in.
DNA is the molecular instructions for life, so it holds all the instructions on how to make every living thing that exists in the world.
It's a very long molecule. Maybe you can look at it as a string.
Body.
You have got two strings that sort of come together and they wind around each other, and on that string you have got four different elements that you can array in a certain arrangement, and they are called A, T, C, and G, and we generally refer to them as DNA base pairs because they bind to each other in a specific way.
DNA origami is a technology which takes DNA molecules and forgets that they have any form of connection to life. It treats them purely as a building material.
So if you forget about everything to do with life in terms of the DNA and try to exploit the only thing of the DNA that it can bind, that it can have two different strands and they can bind together in a programmable way.
It allows us to start building shapes out of this by programming how these elements come together. We're now approaching the era in this field where all the applications are starting to emerge.
Applications are relatively wide-ranging. So if you can imagine, you can make flat things. You can make an origami that is an entirely flat structure, but then you can also make three-dimensional constructs from this.
Some of the applications are in areas such as building molecular structures, but on the other scale, we're moving all the way into things such as diagnostics and medicine.
My research uses DNA origami to sense circulating tumor DNA.
My research is focused on the crystallization of different inorganic components.
In our application, we're using it for diagnostics. And I think what's really rewarding for me and very satisfactory is to really see that our technology has a direct impact in the clinical setup.
Imagine that you can create objects out of DNA that you can put drugs inside of, so little boxes essentially. And on the outside of the box you have targeting agents which bind only to a cancer cell. So when you inject that into your body, this little box travels around, and only when it reaches the cancer cell does the lid open and it release the drug at the target, rather than the chemotherapy that we have nowadays which attacks everything.
And it's sort of still in the development stage, and then when it can actually be implemented in clinics and things like that, I think the impact will be quite big.
I find really exciting the fact that we can use DNA as a building object, so that we can practically use it to build up object on a nanometer scale, which is quite difficult to do in other ways.
The DNA Origami Iris project, it's a very exciting, very interesting project which will give you loads of different skills, not only in computer science, but also in understanding the biology, but in thinking of things in terms of chemical engineering and the physics of how objects interact and work at these length scales.
Caves in and we wash up on the shore.
did you enjoy practical lessons at school, like woodwork and metalwork? Well, here's something you probably didn't have as a hands-on subject: DNA. 2 Yorkshire schools have been taking part in a project which has pupils shaping microscopic structure which could change the face of medicine. Our reporter, Kathy Killick, donned her lab coat and headed off to St John Fisher Catholic Academy in Dewsbury.
But the work they're doing is postgraduate university-level material science. It's called DNA origami. They're taking individual segments of DNA and merging them together to build microscopic shapes they've designed. It's cutting-edge science designed to inspire as much as educate.
It's been amazing. It's given me a chance to, get more analytical skills and get into research and topics which could be studied at PhD.
I do textiles, and my textiles project currently is on chemistry. So it's allowed me to expand in other subjects as well.
I'm genuinely finding the research behind all of this and research into vaccines and everything like that so interesting. So it's really has opened a door for me.
How can so much information be contained in such an exceedingly tiny space?
It's more than 50 years since Crick and Watson discovered the double helix structure of DNA. Now we can pull apart the helix and use its segments as building blocks to make something new.
So balance the tip on the inside of the tube.
Andy Lee is from the Bragg Centre for Materials Research at the University of Leeds. He's helping teach lab techniques and technologies unheard of just 10 years ago, essentially programming DNA to build itself into whatever they want. In this case, smiley faces. What else?
There's lots of really fascinating topics that are not touched on in textbooks, and it's my life's passion to actually pass that information on and get people as excited about those as I am.
They are creating, smiley faces that are 100 nanometers across. So you're talking a molecule that's made of nearly 500,000 atoms. But once again, the scale of it is, you could fit, a few million of them in the side of a pencil. But they're doing all of that in our lab. That, to me, has blown their minds.
Scientists these days need to start young. This project hopes to capture capable minds and coax them into science careers where they can make new discoveries of their own. Kathy Killick, BBC Look North, Dewsbury.
There's a light if you dare to believe it. The floods in and washes all away. Blood, sweat and tears won't retrieve it. You just have to wait to receive the light if you dare to believe it. The floods in and washes all away. Blood, sweat and tears won't retrieve it. You just have to wait to receive it. Blood, sweat and tears won't retrieve it. You just have to wait to receive it. Blood, sweat and tears won't retrieve it. You just have to wait to receive it.
Okay, thank you, everybody. I'm sorry to tear you away from the coffee bar. Hopefully everyone's got a bit of fuel in them now. So to finish off with our final session, but by no means the least, we're on multiscale materials now. And to kick that off, I'd like to introduce Professor Susan Burnell.
Good afternoon, everyone. Thank you very much to the Bragg Centre for allowing me to present this afternoon some of the topics of research I developed with my group at the School of Civil Engineering here at the University of Leeds. So, well, now that everyone is fueled with coffee, happy to see a lot of person alive, I hope that this topic is also interesting to you. So actually, when I was looking at the title of my presentation, I thought that I was going to get into a lot of trouble because it's a mouthful. It says, material science need for transforming construction sector. So perhaps to lower a little bit your expectations, I'm going just to give a perspective. So when we think about concrete, we sometimes forget that this is the most widely used material in the planet, and a person in a lifetime will consume more concrete than food or water. And then when we think about climate change, we often also think about the catastrophic effect that it will have in our natural environment. But we often overlook the effect of climate change in our built environment. And the thing is, because we consume so much concrete, any problem that we have with concrete has a tremendous impact at a global scale. Is that the point that restore and improving our existing infrastructure, not even developing any new infrastructure, just preserving the one we already have, is considered one of the 14 grand challenges for engineering of the 21st century. So I hope that scares us all a little bit about the dimension of the problem. So here, because some people like to see some numbers, I'm just showing some values actually from 10 years ago. These numbers have grown almost double in the past 10 years. So if we think about the cost of infrastructure in a country like the US, it's tremendous. And this is just the cost of the damage caused by one single degradation mechanism that can happen within concrete, which is the corrosion of the steel rebar. So we are not even talking about what happened with concrete. So if we see and we compare these, for example, with the cost of the medical cost in a country like the US, they don't have everything is private healthcare with smoking, obesity, and even if we account the tremendous impact of climate change in, for example, damaging buildings, houses, and so on and so forth, you can see that the cost of infrastructure damage is tremendous. When we think about the UK, almost 60 to 70% of our annual infrastructure budget go to the repair, maintenance, or replacement of infrastructure. So we're talking about quite a lot of £1 billion every year trying to keep things rolling. And I will say more concerning now that we face all these challenges with net zero, sustainability, and so on and so forth. One of the private reports from government actually has mentioned that the construction industry has been described as not fit for purpose in the face of the current challenges. That's tremendously concerning as well. But also, we need to think that business as usual is no longer an option. So we really need to start changing our mindset about how we see our construction sector. So one of the perspectives that have been suggested is that we need to rethink the relationship between the natural and the built environment. We cannot continue treating them completely separated from one another, because in the very end, the built environment is our adaptation of the natural environment to fulfill our social needs. So we need to think about solutions that will work in the longer term for both of them. The other thing is organizational changes. For example, we need to think about how we conceive a construction project. We can no longer just think about building for the sake of building. We need to think about the functionality and also how can we make a construction project sustainable in the longer term. Finally, and more relevant for this specific symposium, is that we need urgently changes of production of the different construction materials that we use, and also in the construction sites. But also, we need to question ourselves. Do we need technological choices? Do we have them? So we need to make just different choices in specific situations, or we need new materials that will fulfill the different needs that we might have for future infrastructure challenges. So, because the talk starts like a little bit dramatic and in the dark side, I want to say there is hope. So one of the things that we can do is actually use the amazing knowledge that we have in material science and engineering to contribute and to support a sector that gives so much back to our society. So today, I'm just going to talk about 4 opportunities of research in material science that tackle some of the challenges I mentioned before, and of course, highlighting some of the research I currently do here at the University of Leeds. So one of the first things, and I will say one of the most widely accepted strategies to support the construction sector, is the development of low-carbon materials. So for those that are not familiar with concrete, concrete is made of Poland cement, which is the glue that keeps the rocks together and gives us that fabulous strength to make buildings and roads and so on and so forth. So one of the most polluting materials within concrete is the cement or that glue. So when we think about low carbon materials, we need to think about, can we use something that is not cement, but behave like cement to produce concrete? And the answer is yes, we can do that. So here I'm just highlighting how when we consider the chemistry of Poland cement-based materials, we can come up with complete different alternatives. So, for example, calcium sulfoaluminate cement, alkali activated materials, inorganic polymers, or geopolymers. So the main difference between Poland cement and this new type of cement, or alternative cement, is the process of manufacturing. So for Poland cement, we need ultra-high temperatures of up to 1,500 degrees during the calcination process. To produce alkali-activated materials, we do this at room temperatures, with the added advantage that we use waste or byproducts from many different industries as the precursors or feedstocks for their production. So here I'm showing a graphic by the Concrete Centre in the UK, where we can see the relative CO2 by cubic meter of concrete produced with this new type of cement. So we can see, for example, that when we use alkali-activated materials, we can have environmental savings between 40 to 80% compared with a Poland cement-based concrete. So that's really appealing. And then one might wonder, why not everyone is using alkali-activated cements if they offer these environmental savings? But the thing is, we still don't have the inside knowledge about how the material will perform in the longer term. And also because it's a material produced by a chemical reaction, a very conservative industry doesn't really like to make such a jump and shift from buying a powder in a bag that you mix with water, you produce your concrete, to start handling a lot of corrosive chemicals. So as soon as I say to someone, oh, we need sodium hydroxide, that perhaps for material scientists is something well understood, they immediately say, no, no, no. Or as soon as you talk about calcium or anything chemistry, people get a little bit scared about. So we need to think about solutions that actually will fulfill the needs of this industry, but that will also work for them. So one of the things we're doing in my group is actually develop something that we call one-part alkali-activated materials. So often the process of alkali activation is you have your powder, you have your liquid alkali solution, blend them, you get your synthetic rock. At the moment, what we're trying to do is creating a sufficiently reactive powder that we mix with water and we produce a cement. So in this way, when in a construction project, if someone wants to produce concrete, they can purchase like the green cement without knowing that was produced in a completely different fashion to the Poland cement that they have used for a very, very long time. But this is not trivial, and this is the main topic of a fellowship that I'm currently developing within my team. So I cluster this research. What are the challenges, the novelty, and the outcomes? So for example, when we decided to tackle this particular problem, we need to ask ourselves, can we produce these materials in a different way? The answer, fortunately, is yes. And we have been working really hard to demonstrate that. But then we need to think about how can we scale up some of these processes that work really well at tiny scales in the lab into bulk, because we're talking about thousands of tons of material that need to be produced every year. Another challenge we have is that when we use waste from different industries, of course, they have tremendous variability. So how can we understand the effect of different impurities that might be in this waste to make our new cement as robust as the Poland cement that you can buy in a hardware store? So one of the approaches that we use is understanding the microstructure. So if we understand the correlation between the chemistry of the raw materials and how the different processing affect the microstructure, we somehow can predict how the material will perform in a bulk scale. Or that's the intention. For doing that, the tricky thing is a lot of the conventional characterization techniques that we use do not work very well for these systems because they are very amorphous, polycrystalline, sometimes contain a lot of impurities. So we need to be very creative with the different analytical techniques that we use. Finally, we cannot just claim that our material is green. We need to actually evaluate this somehow, because we can't just give a green credentials to a material based on what we think is actually doable. The most important thing is when we design a concrete structure, we design it to last 50 to 100 years. So we need to think beyond just the manufacturing process, and we need to think how that structure will interact with the environment. So just to show you another example, a practical example of development of low carbon materials, at the moment my team and I are working with different contractors here in the UK in collaboration with EPFL from Switzerland, and we're using the waste soils from the tunneling works in London to develop a material that can be used to substitute cement within concrete, so they can produce the concrete that then will be used for producing the tunnel. So this one is the Reloop process, because we're thinking about here not just about the applicability of the material science to produce a low carbon material, but also about the circularity of the process. So surprisingly, the main waste that is produced during a major infrastructure project is actually soil, because they need to dig tons of it, and you can't do anything with it. You just have to move it somewhere else. So this project is looking at how can we excavate the soil, treat it, use it to produce concrete, and it will be like zero waste. It's quite exciting project that we're developing. So please visit the poster from Alistair, where he will showcase some of the work we have been doing to characterize these very, very tricky soils, I have to say. The second thing to consider is the resilience of the materials in the stage of design. As I say, we need to consider climate change and the effect that is having on our built environment. So this is just an illustration to show the complexity of the problem that we actually face in the material science of concrete durability. So we have a composite material that has like a solid phase. We have pores. We have a pore solution in the pore, so it's partially saturated. And then we have all these different types of elements that can enter the material. And anything that enters concrete will damage it. So perhaps the most damaging thing is actually carbon dioxide, which is present in the air. We can't isolate our buildings from air. So at the moment, a lot of our crumbling infrastructure is being deteriorated because of the increase in CO2 levels that we have in environment. So when we think about resilience, we need to think about how can we protect our concrete so it will not be damaged by all these things. So first, this is a physical and a chemical process. So we need to understand the transport properties of our porous composite material, and one of the techniques we use very often is X-ray microtomography. So here I'm showing some results of synchrotron X-ray microtomography of different cement samples, and we can see how the pore structure changes over time. So on the top one, we have just a freshly beautiful newborn cement, 1 day old. And at the very bottom, we have a pollen cement after 1 year. So this is also very important because sometimes people think that concrete is static, that once you produce it, it hardens, it's just there. And actually it's not. The reactions continue happening over time, and the properties of the material change over time, which makes it very challenging for us to do any sort of prediction. But however, using advanced materials characterization, we can gain insight about tortuosities over time, diffusivity of different species within concrete, and then use that information to inform the chemical processes about how they're going to proceed. So in good news, a few years ago, with one of my colleagues, we developed actually a type of cement that withstand CO2 exposure. So this type of cement was produced by adding like smart nanoparticles of layer double hydroxides, which are very well known for catalyst processes, but also they bind CO2 within the structure. So if we add these nanoseeds within our cements, actually it has a double effect. It helps to chemically bind CO2, but also it promotes the formation of more layered double hydroxide within the system, making the concrete or the cement more resistant to CO2. So this was quite novel because for these alkali activated materials, it's like the perfect storm. You have very high alkalinity, it will absorb a lot of CO2, so they're very vulnerable to carbonation. But then for the first time, we developed one material that, yes, it will carbonate, but it doesn't lose the loading or the mechanical properties, which in the end is what we want. If it absorbs CO2, it's great, but we don't want the mechanical performance of the material to decay over time. So when we think about resilient materials design, as I say, we need to think about so many different aspects, and we need to consider the chemistry, nanostructure, macrostructure, ion transport option, and of course, the structure's performance, which is the job of my colleagues that are structural engineers in civil engineering, and I confess that I know very little about that. So I'm not going to discuss about that today. Another case of study is materials informatics. So we often, nowadays, we hear a lot about artificial intelligence, machine learning, and so on and so forth. And of course, the construction sector is very keen to use all these tools, particularly because it's a very conservative sector. So for new materials, even though they have green credentials, they will not be utilized because they don't enjoy of the long track record performance for them to say, yes, I can put this material for my bridge that has to last 100 years. So we need to provide the evidence that these materials can withstand these type of environments. So within my group, we use a lot thermodynamic modeling simulations to predict the type of phases and the amount of phases that will be produced in different cements as a function of what we call hydration of reaction time. So you see that timescales we use are actually quite large. And also just for clarification, CSH is not carbon, sulfur, hydrogen. In cement notation, it's calcium silicate hydrate. So please don't panic. We're not creating anything very strange here. But also, these type of thermodynamic simulations allow us to not just see how much or how quickly our cement can react, but also what is the fraction of pores and what is the fraction of the liquid form that is within the cement as it continues reacting. So we can also now simulate, for example, how for a given time that cement will respond when it's exposed to different environments. So a lot of my work actually is focused on understanding the interaction of cement and concrete with carbon dioxide, a process known as carbonation. So we will know, for example, as a function of time, how the microstructure of my material is going to change, and of course, what implications that will have in the changes in porosity within the material. So most recently, one of the projects that I'm developing with one of the PhD researchers working with me is actually combining the thermodynamic simulations with transport modeling. So we can then identify when and how will the CO2 will come into the concrete. So the overall aim of this project is developing like a modeling framework that will enable us to design concrete with the highest capacity of capturing CO2 without damaging the performance of the concrete, but also it will help us to inform that perhaps we need a trade-off between the input of green credential at the moment we produce a cement and how long that cement or concrete is going to last over 50 years. So it will enable us to do quite a lot of interesting work. Fingers crossed, we still have a couple of years to move forward. And then perhaps to inspire all the attendees today, we can actually do quite beautiful and exciting things with concrete. So we can, at the moment, we're looking to produce concrete with different functionalities. So the work I'm going to present now is not mine. But for example, a lot of people is talking about electrically conductive concrete. This has tremendous applications, for example, for concrete pavements. So we will never use the ice and salt anymore. We can just heat up our concrete and the snow will melt. So this is achieved by using carbon fibers, but some people is also starting to work with graphene concretes to make them electrically conductive. Also, I think this is quite beautiful, the glowing concrete. I really like it because, well, it saves a lot of electricity, it's appealing to the eyes, but also it really can contribute in places when we want to enhance safety, but we don't have sufficient electricity to do so. And I will say this is quite novel. It's a translucent concrete. So, for example, it's producing concrete structures, taking advantage of the mechanical properties of concrete and also all the different properties of concrete, but then behaving almost like a glass. So it's a really exciting development within the construction sector that also likes to facilitate the process of construction in the best way they can. And yeah, that's me. So I just would like to thank some of the people that had worked with me, and I present the results from there today. So, and also the different funding bodies that has sponsored my research. Thank you very much.
Thank you. Wow. Translucent concrete. That completely blows my mind. Is there any questions at all for Susan? Fiona.
At the moment, what they're looking for is that it's tremendously cheap, because the cement we produce at the moment is a commodity. We're looking for that it's sustainable, so very low CO2 emissions, and also that it had the capability for producing a very resilient material against all the climate change threats.
But I kind of meant, what sort of materials fulfill your requirements?
At the moment, none of them. Or at least
where are you starting in kind of looking for your ideal material? What sort of materials might fulfill what you're looking for?
Well, I will say that what I'm looking for, the materials will be the ones I am studying at the moment, which are the alkali activated cements, because it ticks quite a lot of the boxes that we need, like is environmentally friendly, made from waste, and so on and so forth. But also the problem with, as I say, the uptake of the technology is the scale up for the construction sector, and also the lack of long-term track record in terms of durability performance.
So can any material be a cement?
No.
You're not narrowing it down for me as to what kind of material can a cement be?
Well, sorry, I don't get what you're asking.
What is cement? I mean, how do you define this, and how are you going to pick your ideal one?
Well, I will define cement, as I say, it's just a binder, it's just a glue. But if I go from the material science, it's just a ceramic type material that is produced by a sintering process.
So you just look for them in terms of trial and error? Or can you say, oh, maybe that material will be a better cement than another one? If it's got a smaller particle size, or maybe this composition would be better, or it's just trial and error?
It's too complicated, to be honest, because if we think about particle size, yes, we can reduce particle size, enhance reactivity, and have some beneficiation from that. But in the chemical sense, the material will perform the same because the same type of reaction products will form when it hydrates. So it's not, I don't have a simple answer to your question. There is no simple answer.
Okay, thank you. I think there was another couple of questions over here. So, Giles, I think.
Thanks. I really enjoyed that talk. Having spent most of Christmas digging big lumps of clay out of my garden to plant rhododendrons, I'm fascinated by how you can use the waste soil to create new types of building materials. But can you say a little bit more about the amount of energy and processing and chemical waste that needs to go into that? And is it really going to be worth the while in terms of the environment to follow that route? Maybe I should have a look at Alice's poster, of course.
Do you mean the process that we're doing with the soils?
Yes, right, yes.
Well, just to give you an example, for producing, as I mentioned, to produce Poland cement is a process that we need 1,500 degrees for roughly 5 hours to produce a reactive cement. For the soils, we can treat them for 2 hours at 800 degrees and make them chemically reactive. So just for the reduction in temperatures that we need and duration of exposure to high temperature, we have tremendous environmental savings. But also, we often think about energy savings or CO2 savings, and we don't think about other potential impacts that we can have. But the reality is that the soil waste also causes impact in terms of land usage, and also many times also in land contamination, because if we have like norms or naturally occurring radioactive materials that we dig up from the ground to the surface, that's another type of environmental impact we can have. So I will say we need to look at this from many different perspectives. But I will say that if a company like HS2 is looking into this like one of the most promising strategies for them to lower the environmental impact of the processes, it's because it's offering quite significant savings.
Okay, thank you. I think for time we should probably skip on as well. And any questions? I think Susan is still around very briefly before she has to depart to collect her son. But thank you, Susan, if you'd like to join me. Okay, so I'd like to call on our final posters, please, for our final lightning round. Sorry. Apologies. Okay, so up first we have Alistair, who can maybe answer Giles's question.
I feel like half my slides are already done for me, but that's fine. So as Professor Bernal said, there is an urgent need to decarbonise the cement sector, which accounts for approximately 6% of all human-made CO2 emissions at the moment. And one way to reduce that, which has just been talked about, is to partially replace that cement with calcined clay, i.e. clay that we've heated to 700, 800 degrees C. And a widespread source of clays is subsoils, including excavation wastes, which are shown there. What largely controls the reactivity of calcined clays and how effective they are is the aluminium coordination in the octahedral sites. And we normally measure this using solid-state NMR, which is often fine, but a bit of a problem for iron-rich soils. NMRs don't like paramagnetic atoms. So to get around this, we're trying an alternative technique, that is using electron energy loss spectroscopy in a TEM to investigate that aluminium coordination in these iron-rich environments. This also has the added benefit of getting locally specific information rather than just being a bulk technique for the whole. So the results so far are quite interesting, promising, and we'll be happy to tell you more if you swing by our poster.
Thank you. Next up is Thomas.
Hi, I'm Tom. I'm a PhD student in School of Chemistry under Dr. Robert Menzel. My work's focused on the fabrication of macroporous metallic films. So what we've been looking at is using microfluidics to fabricate polymer microbeads, which are then used as sacrificial templates in the fabrication of these copper films. And the idea behind this is that they are we can use them to make sort of bespoke sort of copper films with specific controllable, tunable densities, porosities, and void sizes. And these sort of really highly controlled uniform materials are of interest in nuclear fusion research, which is to do with my industrial sponsors, AWE. So yeah, come to my poster if you want to hear a bit more. Cheers.
Thank you very much. And last but not least, we have Mohammed.
Hi. Mucopolysaccharidosis 4 type A is a rare metabolic disorder where the body is unable to process specific sugars called glycoaminoglycans, which leads to the accumulation in cells. It manifests into abnormal skeletal development and dental abnormalities such as dental enamel thinning and dental enamel flaking at the enamel dentine junction, or EDJ. Our aim is to characterize the effects of mucopolysaccharidosis 4 type A on the crystallography of dental enamel using synchrotron diffraction or X-ray, synchrotron X-ray diffraction via the 2ID D-beam line of Argonne National Laboratory Advanced Photon Source in the US. Using this technique, we were able to obtain results regarding texture direction and texture magnitude of hydroxyapatite crystallites from which enamel is made of. Our results, which I'm happy to discuss during the poster sessions, shows interesting differences between the affected and healthy enamel, which is a step forward towards, hopefully, early diagnosis of the disease and the subsequent early prevention and treatment. Thank you very much.
Thank you. Well, that's it. Thank you. Thank you, everyone, for your attention all day. Thank you, everyone, for joining us and being here in person for the Bragg Exchange, the first edition of the Bragg Exchange, but it's the remodeled Bragg Symposium. So hopefully it's been an enjoyable day for everybody. It's not quite over yet. We do have a little bit extra to go see some posters. So hopefully you'll indulge some extra time with the Bragg Centre and follow us over to join us in the Sir William Henry Bragg building for wine, beer, orange juice, whatever your pleasure is, and to talk to our posters about some more details.
Don't sell every drink. I think there's only a limited number.
That is what is there. But so yes, hopefully everyone has had a wonderful day, a stimulating day. We've had some amazing talks across a huge breadth of work that really covers everything that the centre has to offer. I'd particularly like to thank our guest speakers for making the trip over to join us, and I hope that it's been worth the time to visit the centre. We really do appreciate the time and effort that you've taken to visit us. And with that, I've spoken quite a lot today, so I'm going to hand over to our director, Edmund, to finish off proceedings.
I'm not sure I can ever follow Andy, really, but I will try. So, again, I would just reiterate Andy's thanks to you. I think, this is a first thing for the Bragg to have this meeting of this form, and I think we'd all very much welcome, both whether you're in person or online, any feedback you've got. We would love to know more about what you thought, and also what you'd like to think might happen in a year's time. So it would be very useful to have your thoughts about that. And as always with the Bragg Centre, if you've got suggestions for things you'd like to see us doing, please do let us know. So I'm going to join Andy in thanking you all for coming. Thank you for all for your participation, for the questions, for the speakers, for the lightning talks, and also the posters which we're about to go and see. So thank you very much for that. And I'm also going to thank, again, Andy, Lucy, Dan, who have all been helping making this work today, and thank you very much for doing that. So thank you all, and looking forward to seeing you for a drink in a couple of minutes' time over in the Bragg building, and we're looking forward to showing that to you for those who have not been there already. So thank you very much, everyone, and have a good journey back.